Welcome to day 4 of the tutorial. So today, here's just starting with some logistics for the day. So today we're going to start a series of more specialized lectures, or we'll get into chemistry, chem, WACM. We'll learn about paleoclimate. We'll have another component lecture actually on land ice modeling, and then we'll learn about climate variability. We're going to do the Diagnostics Lab exercise today. But of course, as we say, oh wait, before I move on to the next slide, also today is our special longer break in the morning where it's gonna be 30 minutes and we're gonna have a lot of donuts. And then people from the lab are gonna be coming in to meet you and network with you from different topics, and there'll be signs of those different topics out here. So yeah, it'll be great. Do you want to say anything else?
Just a few logistics. If you haven't been receiving the surveys, let me know so that I can make sure that you get them. And we are asking if you haven't done Monday, Tuesday, Wednesday yet and you'd still like to, then please go ahead and do them, but do them by the end of today because today I'm going to start tallying and we will have a daily survey tomorrow that will count towards the raffle. But the full tutorial does not count towards the raffle. We want you to put some extra time and thought into that. Yeah, that's right. Oh, and there's still spots to sign up for Meet an Expert at lunch. Today's the last lunch for that, but no tour today at lunch. The last tour is tomorrow.
And just, yeah, regarding the lab today on diagnostics, today, this is where if you're going to start the diagnostic section today, it's, kind of choosing your own path a little bit now, getting into maybe the components that you're more interested in first, and then working on the other parts if you have time. But of course, it's a self-paced lab. So if you're still working on days 1 through 3, which, we do recommend completing those before moving on to the next one, totally fine to ask questions about that today. Yeah, do we have any logistics questions about today? Oh yeah, no coffee until the second break. Sorry. Okay, then I think we can get started with our first lecture then. Oh yeah. So our first lecture, specialized lecture today, from Rebecca Buchholz, who's a scientist in the Atmospheric Chemistry Observations and Modeling Lab, or ACOM.
Is that on? Is that on? No? No? Yep. I'm getting the thumbs up. That's great. And is that in the right spot, Chris? That maple? Yeah. Okay. Oh my gosh. Okay. All right, I'm going to start a timer here to make sure I keep on time. And great. Good morning. My name is Rebecca Buchholz. I'm a scientist in the Atmospheric Chemistry Observations and Modeling Laboratory here at NCAR. And I'm going to talk today for about 20 minutes on chemistry, which I'm really excited about, chemistry and aerosol modeling in CESM. And while I'm presenting the work that you'll be seeing here today, I really wanted to acknowledge that the contributions from a lot of people added to these slide decks because the model, as you know, is a huge system, and the chemistry and aerosol part is also contributed to by a lot of people. I also wanted to mention that we have this chemistry aerosol working group within CESM. And so our co-chairs are Simona Tilms and Rafa Fernandez. Our software engineer is Francis Vitt, and I'm the liaison, the community liaison, along with Sean Hornemichael as well. And one of Sean's responsibilities is to actually keep the chemical forecast running for the WACM chemical forecast. And on the right there in the background, we have the chemical forecast for last Friday. And this is showing the fire tracer in the chemical forecast. So if you have been wondering why it's been so hazy around here recently, it's because of fires in the region. So in the middle of that plot, we can see really high fire traces in Colorado and the surrounding states coming from local fires. So this kind of motivation to understand air quality, I'll keep on with the motivational slides of like why we want to study and model atmospheric chemistry and aerosols. We have health reasons why we want to look at atmospheric chemistry. So ozone pollution, for example, at the surface is damaging to human tissue as well as vegetation as well. It can damage crops, and so it's a secondary pollutant. It's created in the atmosphere from primary emissions of other chemical species. And we also have particulate matter, so that's an aerosol, and PM2.5 is the health relevant aerosol, which is smaller than 2.5 microns, and it really gets deep into the lungs and can cause cardiovascular issues and have mortality impacts. And so these are two species that we're really concerned about in terms of health. And so understanding the different sources like fires, traffic, anthropogenic sources, farmlands, vegetation, dust and volcanoes, and understand how those different sources contribute to these potential health impacts is something that atmospheric chemistry and aerosol modeling can help with. The other motivation I wanted to touch on was connections to climate, and in something like the Earth System Model, Community Earth System Model, CESM, this is really something we can explore with chemistry and aerosols as well, the interaction between chemistry and aerosols and weather and climate. And we know that CO2 is important for climate impacts, but there's also methane and ozone and aerosols that have climate interactions and influence on temperatures as well. There's the importance of aerosol cloud interactions. You need to have cloud condensation nuclei for clouds to form. Those are aerosols. And so there is all this interaction between chemistry and aerosols and weather and climate. And then finally, the other motivation I wanted to touch on was the ozone layer and the ozone hole. So the stratospheric ozone protects us from UV radiation. And in the 80s, they found that there was a depletion in the Antarctic called the ozone hole, and the ozone hole has been slowly recovering. A modeling study helped understand that there was a missing source of ozone depleting substances and helped identify an area where we needed to mitigate those sources. So really understanding how the ozone hole is recovering is something that modeling can help us with as well. So those are some reasons why we want to look at modeling atmospheric chemistry in a model like the Community Earth System Model. What I'm going to talk about now is how we do that in CSM3. We're going to go through all of these processes that are kind of depicted in this diagram on the left, and we'll go through this pretty quickly. I'll be presenting a lot of information. It's going to be the first time you see this information. And think of it as a first point of call. There'll be references, there'll be support at the end. We'll have like a wiki page link and other references that you can go to find more information about the chemistry that's introduced in this talk. Okay. So CESM, as a global model, has these kind of boxes that we think about. And I like to think about things changing in these boxes as associated with chemistry and aerosols. So if we think of a chemical constituent in a box, we have the change in that chemical over time is just a function of all the sources and sinks of that chemical. So we have emissions and deposition, we have transport in and out, we have transport up, and we also have chemical transformation and chemical loss in that box. And so this equation is an equation from Introduction to Atmospheric Chemistry by Daniel Jacob, and we have the list of things we're going to go through there. And so we're going to step by step through this equation and look at this in CSM. Oh, that's the other point. So if you think about this global model with all these grid boxes, vertically, horizontally, everywhere, and you start to put in hundreds of chemicals, if not thousands, that are actually reacting in the atmosphere. At each time point, at each grid box, this can get really expensive really fast. So when we're thinking about experiments and answering questions, research questions, we want to actually have a balance between chemical complexity and model cost. And so you will see that we have several different atmospheric chemical mechanisms available depending on the cost you want in your model. So we'll get to that. Okay, so the first thing I want to talk about is emissions and how we look at this in CESM. There are four main types of emissions in CESM. We have surface emissions, so these are files that have 2D latitude, longitude, and then by time, surface emissions read into the model. There are also vertical emissions, so 3D gridded emissions per time point that are read into the model as well. And then we also have some interactive emissions. So these are things that actually actively interact in the model online and produce emissions online in the model. And then finally, for some long-lived species, we have surface concentrations or lower boundary conditions defined. And so these are longer time scale emissions, or longer time scale lifetime species that if we're looking at air quality, we're not necessarily interested in understanding the full chemical evolution of those longer lived species for air quality studies. So I just wanted to mention here fire emissions are available in three different options. The default option is the surface emissions. If you want to put vertical emissions, then you need to create 3D fires. But then we also have the option for CLM to have interactive fires as well. I don't have time to go through all of the different interactive emissions that we have in the model, but I wanted to highlight two interactive emissions that we have. The first is dust. So Danny Lung recently updated our dust scheme, so that's the middle plot here shows the resulting dust from the updated dust scheme. He added in a few more variables to interactively create dust from the CLM module component, and it looks much better compared to observations on the right. The other interactive emissions that I wanted to mention is biogenic. So biogenic emissions uses the online model vegetation and has emissions from that vegetation based on leaf area index, meteorology, soil moisture, and light dependence. And so depending on maybe how many aerosols you have in the model, it can change your biogenic emissions as well. So if you have more shading, you could change the biogenic emissions. So that's something to be aware of, that the configuration of your model can change your biogenic emissions. And as we can see in some areas of North America, biogenic emissions are quite high, like in the southeast. Okay, so that's a little primer on emissions. Now looking at the actual chemistry that's happening in the model. And this is where it's going to get a little bit more complicated. And we're going to spend a lot of time on this part. So we have chemical production and chemical loss, and also aerosol processes as well in this section. So in the troposphere, we have a lot of chemistry happening. This is a diagram that starts to show how complicated it is. We have ozone and OH are kind of the primary oxidants in the atmosphere. They're the primary way that chemicals are chemically cleaned out of the atmosphere. And then we have NMVOCs, non-methane volatile organic compounds. And this is actually a whole class of compounds. Like there are hundreds of carbon-containing compounds in the atmosphere. And so for this one line, it's actually representing a whole lot of different compounds. And so there's a lot of things happening here that we need to describe in terms of photochemistry, gas phase chemistry, heterogeneous chemistry, aqueous chemistry, and gas to aerosol exchange. That's happening in the troposphere. We also have slightly different stratospheric chemistry happening. Like I mentioned, we have ozone depletion, so there is some important ozone depletion mechanisms that we need to capture in our mechanism as well. So heterogeneous reactions and catalytic cycles. And this leads to a whole range of different mechanisms that we have available in CESM. So this is not the whole list here on the right. A broader list of what we have available is at this website at the top, where you can see more descriptions and more details about what is in the different mechanisms. But here is just an example of the different types of mechanisms. So on the left here is a diagram showing how we go from more complicated to less complicated chemistry, the different types of chemicals that are in here, halogens, isoprenes, C3 carbons, etc. And so we go from most complicated to least complicated. And then on the right here is a table describing those chemical mechanisms in a little bit more detail and the number of species you can see on the right-hand side of that table. I highlighted in pink the T1S mechanism. So this is T1 is the tropospheric mechanism numbered 1, and S means it also has stratospheric chemistry in there as well. And this is the default that you get when you ask for a chemistry comp set in CESM. The other thing I wanted to mention here is the T4S. So T4S with comprehensive stratospheric chemistry has a slightly simplified tropospheric chemistry, which might be more valuable if you're looking at longer time period simulations, for example, in CMIP7 simulations. And then when you're looking at doing atmospheric simulations, you always actually need to have chemistry because you always need ozone and aerosols to understand radiative balance. And so even in just plain CAM7, there's specified oxidants with greenhouse gas chemistry. So you have a little bit of chemistry in just CAM7 as well. Okay, I'm doing okay for time here. Oh, back one. So this is another way of looking at it. This is different vertical levels of our model. So we have WACM, which Mi-Jong and Nick are going to talk about in the next lecture a little bit more, but this is our highest model top, and this has the most complex chemistry available because it goes all the way to the top of the atmosphere. Then we have our mid-top and low-top model in CAM-CHEM, and we have, going from left to right again, more complex chemistry to more simplified chemistry on the right. And so this is just another way of looking at the different options that we have in chemistry. I wanted to go a little bit more in detail about some of these chemical mechanisms. So like I said, in CAM7, you still have some specified oxidant, very simple chemistry. What we do here is we run the full chemistry model, save oxidants from that model, and then read them into CAM7. And we need those oxidants to do some of the chemistry that we need to do aerosol aging, etc. New in CAM7 compared to CAM6 is we have actually greenhouse gas chemistry, so oxidation and photolysis of greenhouse gases. And we also have interactive secondary organic aerosol production from biogenic emissions. So we didn't have interaction with the land before. The other chemistry I wanted to touch on briefly was this T4S chemistry compared to the default T1S. And the reason we did this is because we're thinking about larger scale, longer time period simulations. And again, balancing that cost versus chemical complexity. And so what we found here, Jun has done a really nice job of evaluating T1S versus T4S in the model and found that the differences are small enough that we think it's okay to use T4S for these longer time simulations and really get similar results to the full chemistry. So yeah, and then finally, just touching on aerosols again, I know you had a lecture on Monday about aerosols, so I just wanted to remind you we have this MAM4 aerosol scheme in the model, and we have different modes of aerosols that they get grouped into. We have MAM5 that now includes stratospheric sulfate as well. And then just touching more on the secondary organics here. So the secondary organic aerosols, a little bit how they're a little different in different mechanisms. So the top diagram shows how complex the secondary organic aerosols are in a full chemistry mechanism. with 5 volatility bins. But in the simplified chemistry, Chem 7, we still have some parameterizations of secondary organic aerosols and also now interaction with the biogenic emissions. Okay, so we've done emissions in chemistry and aerosols. Transport, all I wanted to mention here is this is the transports that is happening in the model, the transport. Either the free-running model, so the physics that is defined by the model and transporting things within the model, or a nudged version. So a nudged version is going to nudge your model physics towards meteorology reanalysis. So a reanalysis ingests satellite data that makes the reanalysis closer to the real winds and the real temperatures. And so when you're nudging towards those, you really want to reproduce things like field campaigns or emission events that actually happened in the real world. That's when you would want to use a nudge simulation, for example. Okay, and then finally, we look quickly at deposition. So there's both wet deposition and dry deposition. We have this large-scale and convective precipitation. We have uptake of chemical constituents into rain or ice and then precipitated out. So it considers in-cloud and below-cloud scavenging rates, and it's a first-order loss process following this equation here. And there are more references down the bottom for wet deposition. This is just an example of comparing model output with observations of wet deposition. I wanted to mention, I know you had more lecture again on the cloud microphysics on Monday, but mentioning how complex it is and how we need to describe this in the model as well. And then finally, dry deposition. So this is just when air parcels move past surfaces, they deposit chemicals onto those surfaces. And so this follows a resistance model, and it depends on the soil, land type, and the roughness of the surface, whether the chemical will be deposited or not. Okay, so we have all of those different processes in the model and having to decide this balance between chemical complexity and model cost. And then I just wanted to finally give you a slide of more support. So we have this wiki page on chemistry at the top, and this has a lot more information about some of the different components. It also has some examples of how to do some more advanced changes in the model, like say you want to change output or add in a new chemical to your chemical mechanism. It has some examples of how to do that. It's constantly being updated as well, so if you find anything that seems a bit outdated, let us know when we can hopefully update that. The thing I didn't really get to touch on was this regional refinement that we have in the model. So we have this ability to do really fine scale modelling over one region with global scale 1 degree. So 14 kilometres over CONUS, for example, and 1 degree everywhere else. And this gives us like population scale, exposure relevant understanding of pollution at local communities embedded in this consistent model globally, so we can get transported pollution in there as well at the same time. So we also have a wiki that is specific to regional refinement as well that adds on to the chemistry. So on the right here, we also have a forum where you can ask questions, specifically if you have issues with trying to get the model running or some sort of chemistry-specific question. Our contact details are over there as well. And then I think I'm just at time, and I just wanted to leave you with the key takeaways. We want to add atmospheric chemistry and aerosols into models because they feed back into the Earth system. They have impacts on health, weather, and climate. We need to take into account all of these different processes when we're adding atmospheric chemistry and aerosols into the model. And then again, a reminder to using the correct model and configuration to answer the question you might be asking. And with that, I think I'm right at time, and thanks for your attention, and let me know if you have questions. Okay, great. Yeah.
If you wanted to add a new chemical or a new species into the model, how involved would that be? What's everything, the list that you'd have to do?
Yeah, so that's described on the wiki, how to do that, but you would have to, it depends what type of chemical. Some can be more complicated than others, but you would need to add it into the chemical mechanism, so you'd need to know things about like its chemical reaction with OH, with NO3, with any kind of chemical reaction that would have in the atmosphere. For example, something like CO is really quite easy because it only really reacts with OH. So you have CO and OH reacting in the atmosphere to give you CO2 and water. So you'd have all the reactions added in. You'd also need to think about wet deposition and dry deposition and add it into the code in wet deposition and dry deposition as well. And I think that is the main parts that you would add it in. So there's kind of 3 places that you would add it into the code. And in the wiki, it does step you through those main 3 places. Yeah.
Good morning.
Good morning.
Do you know if you can use like a single column version or a regional version if you did say have some really localized field data?
Yeah, for sure. It depends what your question is. So you could use the single column version, almost, like kind of box models on top of each other. You could definitely use the single column version. I haven't personally used the single column version with chemistry, but it should be possible. But then you're just really looking at something in one column. And the regional, with the regional refined, you can actually create a regional refined grid over any part of the world that you're interested in. So
you're still running globally.
and you're still running globally, but it's less expensive elsewhere in the world, and so you're only really doing fine scale over where you're looking at. So yeah, if you have a specific campaign, then you can run that. As long as you have all the input there, right? The meteorology, the emissions that cover your time period.
For your comprehensive lecture, and I wonder that when we assess the model, uh, we can use the satellite data or the ground observation data, but if the chemical species such as the glyoxal, it has a strong dependence inter satellite dependency. Some of the observations shows the large concentration of the glyoxal, but some did not. Then if how does the modeler set the ground truth when sets the model?
Yeah, so I think what I'm hearing you say is, how do you understand the model in the state of measurement uncertainty? So sometimes, for example, satellites might have different suggestions of what glyoxal. Glyoxal is a chemical that comes a lot from biogenic sources. And sometimes it'll have a lot and sometimes it'll have not as many. I mean, one of the considerations you have to have when you're comparing model and observations is looking at comparing them at the same time point. So if you have a satellite overpass, you will need to make sure you have your model output at the same time as your satellite overpass. And then you can account for the sensitivity of satellites by the averaging kernel. So the averaging kernel is something that a lot of satellite observations provide that tell you where the satellite is sensitive to measurements, sensitive to information. So a lot of times satellites can be sensitive in the middle atmosphere, but they really go towards their initial guess closer to the surface. And when you compare the satellite and model observations that way, you're comparing more apples to apples. Is that starting to help you? Yeah, okay, great. We can talk more about comparisons later as well if you like. Yeah. Oh, sorry.
From the online description, we see there are other chemistry models also being implemented into CESM, such as GeoScam. I'm wondering what are the difference between using GeoScam, also ChemCam, and also the Musica in the CESM?
Yeah, so Musica is a framework to have any chemistry at different resolutions. So it's a multi-scale chemistry modeling framework. And so it's the same chemical mechanism that you might have in the global model. You could choose exactly the same chemical mechanism. GeosChem, if you want the GeosChem mechanism in in CESM, that has been now implemented. So instead of like T1S mechanism, it would be the GeosChem mechanism. So T1S is actually the Mozart-based chemical mechanism. Mozart was the previous version of their chemical transport model. And so that chemical mechanism came into CSM, and now we also have the option for GeosChem chemical mechanism as well. So yeah, basically whatever chemical mechanism you want to add in, you can add in as a chemical mechanism file, and GeosChem has been added in. Does that help? Yeah, great.
Under what situation should we use GeoScam, and under which situation should we use the others?
Oh, that's a big question. I don't know. I don't know. I think so. What I would suggest is, yeah, because there are uncertainties in chemical mechanisms, there are potentially more or less chemicals being modeled. I would suggest to run a test case of the region you're interested in and look at which one does better compared to observations. Because the same is true for emission inventories. Different emission inventories are best in different regions, in different parts of the world, in different times. So.
Yeah, so when looking at wildfire impacts, when should we prescribe emissions and versus when should we use interactive wildfires? Are there any advantages and disadvantages of doing that?
Yeah, I would say the interactive wildfire missions in CSM right now are still being developed and experimental. And so the wildfire emissions are not necessarily the wildfire emissions that actually happen if you look at the interactive. It's based on probability of ignition and that kind of thing. So that's more something that you would look if you were looking into the future and how fires might change and how the land would change in the future and then impact fires. So I would say prescribe fires if you want to look at a particular fire event, then definitely use prescribed fire emissions.
Could you elaborate a little bit more about the free running and the nudged and how they differ from each other and when I could choose one over the other?
Yeah, this is a little complicated as well because it can get a bit more complicated with like regional refined simulation as well. But I'll start off with like the global nudged versus free running. So nudged, like I said, is nudged towards reanalysis meteorology. So reanalysis meteorology is satellite observations have been ingested into a model and filled in all the blanks so that all the winds are consistent with what satellites have seen. And so that should really be what the winds were doing at the time. And the model, CSM, has its own physics where it calculates winds and temperatures and stuff based on input to the model. And they might be different to what reality was happening. And so what we want to say is at a certain time point, we want to say, we'll nudge these winds in the model towards the reanalysis a little bit. And we don't necessarily want to replace them because we want there to still be semi-consistent physics in the model for other like convection and that kind of thing, right? And so we just nudge them a little bit towards reality at certain time points. Because if we replace them, then we'll get sort of these step changes in the weather happening. And so that's why we say we just nudge them towards reality. And free running is there's no nudging of the physics in the model towards reality. And the reason we definitely want to do this is in the future we have no observations of what reality would be. And so one example would be we would want to look at a nudged version versus a free running version in the current time period, and on average over a long time period, like I don't know how many years, but decades, what does the weather look like in the free running versus the nudged version? And if they look consistent, then we can be hopeful or we have support that the future experiments will be true. So Does that help? Cool. Am I out of time? Okay. Thank you.
Thank you. Did very well on time.
Oh,
Let's thank
9
Rebecca
exactly.
again.
Thank you.
And now we're going to have a break until 9:15, but we're going to do our group photo now. And maybe Rebecca also can stay a little bit during the break. Okay, for additional questions and discussion.
Yeah.
But if you want to be a part of the group photo, I think we'll take that. We'll take that during this break. So come outside to be a part of it.
Do you want us to do that first? Or do you want us to do that in 5?
Let's. I'm looking where Elizabeth is. Okay, she's out there. Let's all. The ding ding ding. Someone out there. Okay, she did it. All right. Welcome back. We're going to continue on with our next lecture on Wacom and Wacom X. Mijong Park and Nick Petitella are going to give this next lecture. So we'll get started. Thank you.
Hello, can you hear me okay? It's on. Can you hear me now? Okay, awesome. So good morning, everyone. Good morning. I'm Mi Zhong. I'm at ACOM. I'm the Wacom liaison, one and only liaison here. And Nick Petitella is one of the Wacom co-chairs. And at the bottom, I listed a number of people: Francis, June, Martina, Hani, Joe, and Daniele. So we are whole atmosphere working group. So some people are ACOM and some people are HAO, and Daniele is actually from outside. So today, Nick and I are going to introduce you to the whole atmosphere modeling. So I'll start with Wacom, and Nick will take over and let you know everything about Wacom X. He's an expert in Wacom X. And after Nick's presentation, we hope to have some time for questions and more hopefully for some answers for you. So before we dive in, let's take a minute to think about what's the motivation for the whole atmosphere modeling. So the diagram on your right shows various phenomena in the atmosphere, from really short time scale of hours to really long time scale of years or centuries. And on the y-axis, you can see local to regional global scale. On the upper right corner, you can see global weather system and climate. That's where Wacom and Wacom X fit. So Wacom and Wacom X have the middle atmosphere, which means stratosphere and mesosphere. And the middle atmosphere couples, as you can imagine, the lower atmosphere and surface to upper atmosphere. And everything comes with it: chemistry, dynamics, and radiation. And they're all coupled and interacting to each other. So in a perfect world, we need a model that can simulate this coupling: short time scale, long time scale, small scale, and large scale feature. Now, let's look in the vertical structure. So on the figure on the left, you see from the surface going up troposphere, stratosphere, and up to geosphere. I want you to look at the region called MLT. MLT stands for mesosphere and lower thermosphere. And the altitude range is about 50 to 150 kilometers. The general idea of this whole vertical structure is that from the surface, energy propagates up as a form of waves or tides, and also energy is coming into the atmosphere from the space. And so Wacom goes up to about 140 kilometers, and Wacom X even higher up, about 500, even 600 kilometers. So on the right-hand side, these are the ion density figure. I found some in literature. So at the bottom is about 50 kilometers, 60 kilometers. So Wacom includes D and E regions, and Wacom X also includes F region, with chemistry which comes with it. Okay, now you can tell, oh, Wacom and Wacom X is really high. Then you might have a question: hey, where do they fit? Are they just some orphan staying somewhere in the space? I'm sure you're familiar with this figure by now. So these are the CESM 3 component models. The top, so you see CAM, CAM-CAM, Wacom, and Wacom 7, they all fit into atmosphere component in the CSM. I didn't tell you yet, but we're really excited about the CSM 3, Wacom 7, Wacom X version 3. And you might wonder, when or where did they come from? So if you go back really long time ago, there was general circulation model. People try to model the Earth, but they started from really low altitude. So it was not until early 2000, even 1999, the scientists thought we need to go up higher, mainly related to we want to make sure we have the solar forcing impact and even ozone layer to the surface climate. So this is, I looked at all the literature, I came up with this timeline. So on the very left, we have Wacom 1B came out around 2000. Wacom 2, 3, 4. As the version moves on, we've added a bunch of new features. But it was not until Wacom 5, until 2017 also, we were able to generate QBO. QBO, I hope everyone knows about QBO. QBO is such a cool feature. So QBO is dominating feature in the stratosphere and connects different features. It even affects the weather in the troposphere. So we were excited about this feature of internally generated QBO in Wacom 5. And by Wacom 6, it's based on CESM 2, CAM 6. That's when we started having, okay, Wacom is built on top of CAM 6. Everything is the same. We're just going higher up. And now Wacom 7 is 2026. And in terms of Wacom X timeline, Nick can talk more about it later, but it has separate timeline. It came in 2010, and then Wacom X version 2 and 3. We talked about, hey, Wacom X could be same version like Wacom X7, but I think they have decided their own version. So it's going to be Wacom X version 3, which will be released with CSM 3 and Wacom 7. So if you're interested in all these different versions of model, and then you have this listed all the literature you can read about. Then what's really new? So there are so many new features in this new version of Wacom, which is Wacom 7. But one really big change is we have more vertical layers. This is related to, because when CAM was moving from CAM 6 to CAM 7, they added a bunch of layers in the planetary boundary layer. And Wacom has to follow these extra layers in the low altitude. As you can see from this figure, there are 3 different colors. Blue is Wacom 7. You can see 135 level. And black was Wacom 6, was 110 level. And you might have heard about this model, new model, CAM MT, is CAM Meta model. So these models have pretty similar vertical grading up to about 30 kilometers and diverge above. As you can see, why Wacom is more fit than other models, it has finer vertical resolution in the stratosphere and above. And so I just mentioned to you, from Wacom 6, we are sharing the same physical and dynamical core with CAM. So let's look at Wacom 6 and Wacom 7 compare. And some features are still consistent. We're sharing everything from CAM 7, but some features are a little bit different. So the table on the left is showing Wacom 6. It has more bullet points. It doesn't mean that Wacom 7 is much better. So I try to, so some of them we're still keeping it. So altitude, we go up to 140 kilometers. Wacom 6 used to have 70 or 110 level. Now Wacom 7 has 135 level. Wacom 6 used to be based on finite volume dicore. Now we're using spectral element dicore. And chemistry, the basic idea of chemistry in Wacom is, it's up to you, you choose. You want really complicated, complex chemistry, including everything troposphere, everything with atmosphere. We still have that, slightly different name. It used to be TSMLT, troposphere, stratosphere, mesosphere, lower thermosphere. And we have T1MA, we changed a little bit name just to confuse you. And so, and we have some improvement I can go over a little bit later now. If you're interested in, we can do website, the CESM tutorial website, or we have really good documentation you can read about, learn about. But Wacom 6 overall, we have many elements of improved schemes and features you can explore and you can use for your research and project further. So I just have two really cool features I want to emphasize. One of them is called tropospheric ultraviolet and visible. We call TUV. And the improved version is TUVX, which means TUV extended. So I'm not a chemist. And some of you feel like, hey, I'm not a chemist either. I have no idea what we're talking about. But we can try to maybe understand what it does. So what TUV does is it computes photolysis rates. The sun comes in and all the chemicals can break down because of the sun. And what are the rates? And the other things, so photolysis rates are important for ozone and nitrogen oxide and VOCs, as you can imagine. And TUV also calculate how much UV can penetrate the Earth and what altitude it lands. So the table at the bottom, I listed a couple of different elements. So in old TUV, we used until CESM2, which means until Wacom 6. It was based on something called lookup table. So this table, they go, oh, okay, this number, we have to use this. It was not really reflecting how dynamical the air is. They react all the time and it changes all the time. So TUVX is to implement this, calculate the photolysis rate and heating rates in real time, interactively. So as you can imagine, this will have more benefits too, not only in stratosphere, also troposphere as well. So this slide, actually, this is what June is working on. I asked June, hey, can you give me a slide that shows how TUVX is really cool compared to TUV? So there are a bunch of figures, and don't be afraid, and try to just look at what this means. This colorful figure shows there's cloud and aerosols. So clouds and aerosols, we all know they're really complicated because they interact with everything. But in this case, so there's cloud and aerosol. Why? Why is it really complicated? Because sunlight comes in, it can scatter, observe, and reflect. And by doing that, it can affect the photolysis rate. Above the cloud and reflecting sun can increase it, or below, decrease it. Also, when there's aerosol layer, it can change the rate as well. So June kindly put the two figures at the bottom right. This was when 1991, the big Mount Pinatubo volcano went off. The colored line on the left is ozone photolysis rate. Once again, I'm not a chemist, but I'm trying to speak chemical language here. So photolysis rate for ozone, the red line is with aerosol impact. Below, the gray line is aerosol layer. Below, maybe it changes the photolysis rate. On the right is for NO2, photolysis rate. And when there's cloud, it really increases above the cloud because of the scattering. It increases the photolysis rate. So the bottom line of TUVX is to take into account all this impact from cloud and aerosol interactively. You can learn more about it. I think she's working on a paper. Another feature I think is really cool is, how many of you know about CMIP 6 or CMIP 5? The CMIP, okay, awesome. CMIP is Climate Modeling Intercomparison Project. Now we're moving to CMIP 7. So CMIP 6 was really useful. Hey, I don't want to look at only one model. I want to look at what other models are doing. And to be able to do this, what they do is, all the modeling group, they say, hey, can you give me the forcing file? We want to use the same forcing and do the run and see how the different models work differently. And CMIP 6, after moving to CMIP 7 we're working on, we have made some changes. Oh, maybe in CMIP 6, something was not so perfect. Let's work on it. This slide from Ilaria, she's at ACOM as well. She's been working on this new stratospheric aerosol emission database for CMIP 7. On the left, there are a bunch of lines, and whoa, this is too much. I don't want to look at it. But you have to look at it somehow. So and she also made this bullet point. One thing they did for CMIP 7 is they realized when the volcano erupted, they actually dumped the aerosols right below the plumb height. So what she described here is they reduce altitude injection of large volcanoes, and they will help with more accurate impact in the atmosphere. So without looking at the really many different color lines, some are CMF6, some are CMF7 with 1 degree, and black line is observation. GLOSAC means global stratospheric satellite-based stratospheric aerosol climatology, something like that. So good AOD, but some features CMF7 is doing better than CMF6. Some are maybe worse than CMF6, but we're still working on it. And before I give to Nick is ready to come up, but I want to talk about the QBO. This is my favorite feature in the stratosphere. I'm dynamist. So my daughter, I told, I want to talk about QBO with you. And she said, why don't you call Kubo? Why do you call QBO? Quasi-biennial oscillation in stratosphere, it has to be about 26 months, Wesley is changing. So for a really long time, global models really struggle to internally generate this QBO. But about maybe early 2010, 2012, they finally figure out how to generate good QBO in the model. So I put two figures here to demonstrate. Top figure is Wacom 6 70 level version. As you can see, QBO, the orange color Wesley, doesn't come down low enough, so it's not perfect. And how can you make perfect? The key ingredient is we have to have adequate horizontal, vertical resolution, and we have to parameterize convection and gravity waves, all that. And one key element was having about 500-meter vertical resolution in the upper troposphere and lower stratosphere. So Wacom 6, this says Wacom 5, but Wacom 6 110 level version, we have really good QBO. Then how about Wacom 7? We spend so much time tuning this QBO to get the good QBO in Wacom 7. And right now, we have just perfect QBO, beautiful QBO. So on the left, we're looking at zonal mean zonal in the tropics. It comes down and then amplitude is just perfect compared to reanalysis. So we are really excited about Wacom 7. Now, Nick is ready to tell you all about Wacom X. If you have any questions, just hold on to it until Nick is done with his talk.
Okay, thanks, Meizhong. You can hear me okay, I hope. So Meizhong already discussed, I think, a little bit of Wacom X. And essentially, it's a model that extends up into the upper atmosphere, ionosphere, thermosphere, with an upper boundary somewhere around 500 kilometers. So you can see on the right here, kind of the domain of the CAM, Wacom X. And of course, we don't just add extra layers to the model. There's a lot of different processes that we need to account for when we raise it. So some of the different things I'll talk about in a little bit, but we have ion transport because we have this ionized plasma that is moving around, and there's a magnetic field Earth has. And so if you have plasma moving through a magnetic field, you can generate electric fields as well. So that's another thing we need. And then the energetics from the sun are also very different. And you might ask, why are we building Wacom X? CAM is good enough or Wacom is good enough. But really the interest is to look at space weather and effects of both the sun on the upper atmosphere, but also coupling from the lower atmosphere, kind of terrestrial weather and climate, and how that impacts the space environment. So we're looking at sort of coupling mechanisms through chemistry, physics, or dynamics. And then also sort of downward coupling. If you have sort of extreme solar events, how that can eventually sort of couple down into the stratosphere and potentially impact surface climate as well. So kind of coupling in both directions is what we're looking at. And then kind of, like I said, how the sun can impact the Earth system. So Wacom X is another one of these atmosphere components of Wacom, like Wacom or CAM, but it is treated a little bit different because it kind of needs pieces from dynamics and physics. So I think earlier in the week, you maybe learned how the two are separated. You have sort of dynamics and physics. And Wacom, we need a sort of interface between them. So when we developed the model, we built this interface. And then the sort of key thing is that once we take the dynamics information and physics information, we need to put everything into a magnetic coordinate frame, so aligned along the Earth's magnetic grid. and then we can do a sort of electrodynamics calculation to calculate the electric fields, which can drive a lot of the variability. And then we also do a sort of transport of the plasma in geographic coordinates as well. And so then this is all then passed back into dynamics and physics. So it gets a little bit more complicated once we add these extra processes. So for CSM3, I will pause the movie first. So one of the main things, when you extend the dynamical core up into the higher altitudes into the thermosphere, you actually need to modify the dynamical core itself. So in the up to, say, 100 kilometers or so, you can assume that the mean mass of the atmosphere is the same. So because everything is well mixed and the composition is essentially the same. But once you get into the thermosphere, species basically diffuse separately based on their weight, and the mean molecular weight of the atmosphere basically varies with height. So when we just raise the dynamical core upward, we need to account for things like the variable mean mass and also different diffusion and viscosity that occurs in the thermosphere. So the SE dynamical core was extended up into the thermosphere as part of CESM3. And then we have a sort of new capability to do very high resolution simulations. And I will show an example here. This movie is showing the capabilities we get with a high resolution model from the surface all the way to the upper atmosphere. So this is basically there was this underwater volcano, the Hunga Tonga eruption. And so we simulated that in the model. And what you're seeing here, the bottom is basically the surface pressure perturbation from the volcanic eruption. And then the upper part is a perturbation in the ionosphere, this sort of plasma layer around 300 kilometers. And you'll see these sort of waves propagating along the surface, and then also they essentially propagate all the way up into the upper atmosphere. So these are the sort of things we want to study with this sort of model. So here you can see these sort of surface waves from the volcano, and then this sort of upper atmosphere sort of propagating outward, these sort of rings from the gravity waves that propagate all the way up into the thermosphere. And these actually sort of wrap around the Earth. So these are the kind of new things we're able to study now that we have this high resolution capability with a dynamical core that extends up into the ionosphere and thermosphere. So also for CESM3, the chemistry is also a critical part of the upper atmosphere. So we've updated some of the chemistry, and I will show on the next slide why this really matters. So these are the reaction rates we changed. It's mostly related to the nitrogen chemistry. And one of the important sort of parameters of interest in the upper atmosphere is the neutral density. So even though you think, well, once you're at 500 kilometers, there's basically no air, it's a vacuum, there is actually a little bit of density. And we have all these satellites and things flying around Earth, and their orbit is basically perturbed by how dense that atmosphere is. So if it's more or less dense, you have more or less drag. Just like here, I think everyone is familiar. If you throw something, there's some drag force on it. So satellites are experiencing this all the time. And so when we updated the chemistry, the left figure here is basically showing the old chemistry. So this is the density of the atmosphere at 350 kilometers. And with the new chemistry, we got about a 20% decrease in the density. And our previous density turned out to be a little bit too high. So when we ran a scenario here and compared the green line, this is Wacom-X with the new chemistry, just compare the green and the black. So the black is sort of observations. And if you look at our model now with the new chemistry, matches very well the observations. So we're getting the sort of density that would be experienced by satellites much better with our updated chemistry. And that means we can do better understanding of sort of space weather effects on satellites and debris and their sort of orbit propagation. So just in conclusion, some of the comp sets for Wacom and Wacom-X we wanted to just show. So the main ones are these sort of FK, so just with the atmosphere, not coupled ocean with prescribed sea surface temperature. And then there are these different chemistry options of varying complexity and varying cost. So specified chemistry is kind of cheapest. And then we have the middle atmosphere chemistry, which was developed for CSM2 as a sort of cheaper option if you're mostly interested in stratosphere and mesosphere. and then there's sort of T1 and T4. And for Wacom X, the kind of default comp set is this sort of just MA chemistry, which, because the model is much more expensive already, we kind of mostly use just a simplified chemistry. These are the kind of default ones, but there's other configurations, of course, you can kind of build that wouldn't be kind of available right out of the box, but there's other ones that can be used. So I think with that, we will conclude our talk, and we can take any questions, I think. Yeah. Thank you.
I have a question. Just to see if I understood correctly, so the Wacom 6 and 7, they go up to 140 kilometers. Then the 7 has more vertical layers, that's correct? So the vertical layer is finer than the Wacom 6?
Yeah, I think, well, this one actually doesn't have the old one. But yeah, the upper boundary is the same, but the vertical resolution is very different. I don't know what was discussed earlier in the meeting, but Wacom 6 is built off of CAM 6, so it's followed sort of the vertical levels of CAM 6. So in the boundary layer and troposphere, CAM 6 had a coarser resolution. So we've added levels there, and then added also a little bit finer resolution through the stratosphere. So you just have finer vertical resolution, but still the same model top.
How do your setups of these models compare to what operational forecasting uses, and are you working with those groups?
Yeah, that's a good question. I don't know for Wacom if there's as much of a group that does operation stuff, or I don't know if we want to.
Yeah, we don't really do operational forecasts here, but we do have a chemical forecast, and it's right now I think it's Wacom 6, which is running, but we're moving into doing forecasts like imminently.
And for Wacom X, there are groups like NOAA and the Navy have kind of, I don't want to say the same, but similar style of model that would extend from the surface all the way to 500 kilometers, with a modified dynamical core and things like that, but built off of their kind of weather models. The Navy has their weather model, and then they extended it up into the thermosphere, and same thing with NOAA. They sort of extend their tropospheric weather model up into the thermosphere. Some of the details are, of course, different, but the sort of general framework is very similar.
Thank you. I had a question about the QBO. So in this new model with more layers, it does look really, really good in the lower stratosphere. And I was wondering the extent to which in this new model, like the gravity wave parameterization is was that a big thing that you needed to change, or just the vertical resolution made that big change?
So that's a really great question. So QBO, as much as I love QBO,
It's really a little bit complicated in terms of parameterization
of gravity wave, because gravity wave is really hard to really parameterize correctly. So people have been trying in higher vertical resolution. So one thing about the QBO, ILA has a paper. They try to really increase vertical resolution in the upper troposphere, lower stratosphere. If you can really improve the QBO, they try 300, 400, 500, 6, 7, and they found out as long as it's about 500 meter, we have pretty good QBO. So that's the fact. It doesn't matter Wacom 6, 7, or a different model, as long as you have really fine vertical resolution about 500 meter, we can get good QBO. So between Wacom 6 and 7, the number of vertical levels maybe is scary. Oh, we have now 135, maybe we even get even better QBO because we have more layers. But most of the addition was in the bounded layer. Even though the vertical spacing is a little bit smaller than Wacom 6, than in Wacom 7. It doesn't have a huge impact. And in terms of gravity wave parameterization, we were able to use the old Barras parameter and a little bit of tuning. For example, we used to have to really increase the contribution from gravity wave, but now we have maybe less. It's smaller because convection has changed. In CAM, we use something called Zhang-McFarlane convection scheme. That has changed because of this extra boundary layer levels. So really, we spent a lot of time tuning what combination works the best. And we made a little bit of changes to Barras parameter scheme. We had heating depths and Qmax. I'll be in the lab in the afternoon. We can talk more about it later. Because as you all know, QBO really impacts all the phenomena in the atmosphere. And one thing I meant to mention to you, so the COMSAT can be, this is fluid. It's not that we fixed COMSAT, we cannot do anything else. We can add more, and you can come up with your own COMSAT by using long names. And for Wacom, as you can imagine, we have high vertical level, and it's really expensive. And that means is, oh, can I pay for it? No, you need computer resources and it takes time to run. For example, running 1 year take 1 day, then that's really difficult. So we have different version. Instead of using 1 degree horizontal resolution, we have 2 degree. It's coarser, and we're comparing these two setups. If they have really consistent climatology, the features you're interested in, then you can use 2 degree and a little bit simplify chemistry. It saves a lot of computing time, then you can do more runs and you can maybe shorten your time during PhD. So you can be a doctor sooner. So I'm happy to really answer any questions you might have. I didn't list any email address here, but just come find me, talk to me. So thank you.
Okay, great. Let's thank Mijong and Nick again. Now we have our 30-minute break. Go out here and network with the scientists, have a donut, and then come back here at 10:15. All right. Welcome back. Let people settle in a little bit, but we're going to get started with our next specialized lecture. Jiangzhu is a scientist in the paleo and polar climate section, and he's going to talk about paleoclimate.
Okay, thank you, Sophia. Is the sound okay? Okay. Great. Let's get started. Hello, everyone. Welcome to NSF NCAR. I'm Jiangzhu, a scientist here. I'm also the co-chair of CESM Paleoclimate Working Group. Today, I will give you some perspectives on paleoclimate modeling with CESM. Here is the outline. I will spend most of my time on why paleoclimate. Then I will give you a very brief introduction about how to perform paleoclimate simulations with CESM. And a special case for us is the water isotope capability. That's where we co-lead the development of CESM1 capability. And finally, some resources from the CESM Paleoclimate Working Group. So why paleoclimate? We have a lot of data. And at the bottom, you can see the 30 in ice core records from the past 80,000 years. And the 0 means pre-industrial. So you can see if you go back by 10,000 years, the climate is relatively stable. That's the Holocene. If you move further back, we have the deglaciation and then glacial climate. And in this record, you can see a lot of large-scale variations. And warmer, higher values mean warmer temperatures, and they indicate that local temperature could change abruptly by 20 degrees C, up to 20 degrees C in a few decades. So those are really remarkable, abrupt changes. If you move further back, we use sediments in ocean to look at the temperature as well. So you can see the glacial interglacial cycle is not unique. So it's pretty common in the past 2 million years. And for the first part of the 1 million year, interestingly, the magnitude of glacial interglacial cycle is much bigger. The period is around 100K. If you move further back, the magnitude is much reduced. The period is around 41K. If you move further back to 65 million years ago, now you see that what we live in the climate right now is actually pretty special. We are actually living in an ice house climate. So for the majority of the recent Earth's history, the climate was much warmer than right now. And the warmest extreme occurred during the early Eocene, and the global mean surface temperature could be 15 degrees C warmer than right now. So this is really remarkable. And you can also observe some stepwise transition from the hot house to ice house climate. Through showing you the data, and hopefully you can also see that there are a lot of mysteries about climate variation in the Earth's recent past. For example, abrupt climate changes, tipping point behavior, glacial interglacial cycle, and the role of ice sheet carbon cycle feedbacks, greenhouse climates, and the transition to ice house climates, and all the hydroclimate changes associated with those large-scale climate variations. So we have a lot of unsolved mysteries. If you are looking for a climate problem, just pick one, and it will keep your career busy. In the next few slides, I want to convince you that paleoclimate also provides powerful test bed for CESM evaluation and development. I will use 3 simple examples. The first one is about climate sensitivity. So equilibrium climate sensitivity, is the amount of global warming you get if you double the CO2 concentration in the atmosphere. It's a simple metric in climate dynamics, but it is very important. That's why the community has been interested in quantifying this metric for more than 5 decades now. So through decades of efforts, this is our current understanding. Still, there are substantial uncertainty associated with this metric. From CESM perspective, you can plot the model estimated climate sensitivity on top. This is what you get. And you see that in the early version of CESM, the ECS was 2 degrees C, so 2 degrees C warming per doubling. And interestingly, the ECS increases with model version and reaching value almost 6 in the most recent CESM2. Of course, the important question is, are those models realistic? So to address this question, we can use instrumental records to assess the model behavior. So here we are looking at the global warming simulated in the historical simulations using different versions of CESM. And you see that although the ECS among them are so different, but they more or less simulate the 1 degree C global warming during the historical period. And given the uncertainty from internal variability and non-CO2 forcing pattern effect, etc., it's really challenging to make a definitive assessment using instrumental records. Luckily, nature has run the experiment for us. We can use paleoclimate data. This is not a new idea. This is an old idea dated back to Suki Manabe and Broccoli in 1985. So in this paper, they wanted to use the last glacial maximum data to assess model climate sensitivity. So why last glacial maximum? A couple reasons. The first one is that it's very different from the modern climate, meaning that you have a big signal to noise ratio. You don't need to worry too much about the internal variability, for example. The second reason is that it's not that different, not that distant from right now, meaning we have thousands of temperature records that we could take advantage of. And it's a colder climate. Major climate forcing are the lower greenhouse gas concentration and the presence of ice sheets. When you incorporate those forcing into the model, you can perform simulation of the last glacial maximum with CESM. So here, let's focus on the plot on the right. You can see the x-axis is the LGM global cooling. So that's the simulated LGM global mean temperature minus the corresponding pre-industrial simulation. The y-axis is the equilibrium climate sensitivity. And the dots are different CESM versions. You see a remarkable relationship among them. So the higher the model climate sensitivity is, the greater cooling the model will simulate for the last glacial maximum. And the unique advantage of paleoclimate is we have real-world data for the magnitude of LGM cooling. So here we are using Tierney 2020. This suggests that the LGM is 6 degrees C colder roughly than the pre-industrial. Using this data, we can already assess that the lower climate sensitivity is likely unrealistic, and also the high climate sensitivity in CESM2 is also unrealistic. We can take one step further and use the paleoclimate data to identify the issues in CESM and to address that. Based on that, we developed the paleoclimate calibrated CESM2. You can see that the ECS is much lower and the LGM is much more realistic as well. If you compare to the plot on the left, you see that all the model versions, they look like each other if you compare with a modern climate. However, once you take them to a paleoclimate state, they differ substantially. The global mean temperature could differ by 10 degrees C. This is really remarkable differences. And the issues we identified in CESM2 have been corrected in CESM3. So that's the golden star here. And once we, in our preliminary simulations, LGM is very realistic. The ECS is also much lower than CESM2. So this looks very good. The second example is about ocean circulation. So for decades, paleoceanographers have accumulated multiple indicators to derive or reconstruct the large-scale ocean circulation. For example, Atlantic meridional overturning circulation. Hopefully you remember the concept from Peter's talk the other day. This is a major circulation in the ocean. And based on paleo records, they suggest that a shallower and likely weaker AMOC during the LGM. Well, can model reproduce that? Here, we are looking at, again, different CESM model versions. And the top panel is pre-industrial. The bottom panel is LGM. And remarkably, they all simulate a shallower AMOC during the last glacial maximum. For example, you can focus on the zero contour line here. It's much shallower in the LGM simulation. And in CESM3, it is also much weaker. So this agrees very well with paleoclimate data. This is not easy to do. It turns out that CESM is the only model in the PMAP archive that can simulate a shallower AMOC. For example, if you look at the IPSL, this model, and you can see the maximum strength is much deeper, and the AMOC strength is much stronger as well. So it is really interesting that the CESM can simulate the large-scale ocean circulation change at the glacial climate very well. You may wonder why. Our interpretation is that CESM captures the Southern Ocean dynamics and sea ice very well. So basically, the process is if you add a cooling forcing, you have sea ice expansion. And in addition, the brine rejection associated with the sea ice expansion can strengthen the Antarctic bottom water. Both the sea ice expansion and the strengthening of the Antarctic bottom water can contribute to a shallower North Atlantic deep water, thus a shallower AMOC. The third example is about ENSO variability. I believe Clara Desser will give a talk later this afternoon on ENSO. So here I'm only going to give you a very simple paleo flavor about ENSO variability. So now a classical test case for ENSO variability is mid-Holocene, relatively stable global climate. Now the major climate forcing is the seasonal variation in solar insolation. And many paleoclimate records suggest that for the mid-Holocene, maybe 6,000 years ago, the ENSO variability could be much reduced, up to 40%. However, the models in general, they can only capture 10% weakening. For example, if you look at the last column, which is a multiple model mean. So this casts a serious doubts about the model. Do they miss important physics about ENSO dynamics? So here, we use CESM 1.2 to perform mid-Holocene simulation, PMAP-like simulation. And not surprisingly, we can only capture a 10% weakening of the standard deviation associated with ENSO variability. And it's much lower than the proxy suggested 40%. Interestingly, in a sensitivity simulation, if we prescribe a green Sahara in the simulation that's informed by paleo data as well, we can reproduce the level of ENSO reduction in a very good agreement with our proxy data. So this suggests that likely the ENSO dynamics and its response to external forcing is largely okay. In the model, we miss this response seen in proxy data is likely because we don't have a green Sahara forcing. And for CESM, it cannot predict the vegetation, so we have to prescribe that as an external forcing in this case. From a mechanistic perspective, if you add a green Sahara, that's additional heating to the atmosphere based on a Gill-like pattern response that will trigger the easterlies along the equatorial Pacific, which will strengthen the water circulation and damps ENSO variability. So a quick summary so far for the lessons we learned on climate sensitivity. I showed you that paleo help evaluate models and improve parameterizations. From ocean circulation perspective, we find that Southern Ocean dynamics and sea ice are critical. For ENSO variability, we think the model physics is more or less okay, and it stresses the importance of remote land surface forcing, and it can be as important as local dynamics. This has implications for ongoing African greening and the deforestation of Amazon. And there are many, many lessons accumulated over the years by the community. In the interest of time, I'm only showing you the 3 examples here. Through these 3 examples, the message I want to deliver is that CESM family models are the best performing CMIP models in paleoclimate. This should really build our confidence about using the model in future projection and in your research. How to run paleoclimate simulations with CESM? If you want to run mid-Holocene, please go to the lab exercise on Friday. It's actually pretty easy. You change the orbital through name list changes. For CESM3 LGM, it's much more challenging. It involves changing many initial and boundary condition files. Here is a list. I'm happy to tell you that I developed a suite of notebooks to document the development of boundary condition, the whole processes. It's preliminary, but it's available right now on GitHub. Feel free to take a look if you are interested. And I also gave a talk earlier this year at CESM Paleoclimate Working Group meeting. You can also find the recording on YouTube. If you want to use older versions of CESM, you can use the Paleo Toolkit, but please be remember that this is no longer supported. One special contribution to CESM development is the water isotope capability. Hopefully you already noticed that in the paleo data I showed you earlier, most of them are in the oxygen isotope units. That's why we co-lead the isotope capability in CESM1. So here is a diagram of isotope-enabled CESM1. How does this work? Basically, we go to the CESM, the normal code, we replicate the water cycle. And then we introduce fractionations when needed. So the fractionations, that's what makes a difference for heavier isotopes when you compare with the normal isotopes. Then we can have the isotope-enabled CESM. Basically, we follow the hydrological processes as closely as possible to the regular water cycle. So those are a list of processes included. And one thing I think worth highlighting is the moisture tracking capability, thanks to Jesse who developed this. So basically, using this capability, you can track the moisture after they are evaporated from a particular ocean surface or land surfaces. This is remarkably useful capability. And if you want to use the code, it's available on GitHub. And if you want to run the model, go to the lab exercise on Friday. And you can see that the current isotope capability is in CESM1. The physics has been more than 15 years old now. So luckily, we are funded by NSF to develop the next generation isotope-enabled CESM3. So we will use modern practice in the code development and management. The goal is to add isotope code into the main trunk of CESM this time. We will focus on the isotopic water cycle and also enhance this important water tracking functionality. If you are interested in helping us developing and testing the model, please reach out. Some resources from CESM Paleoclimate Working Group. Here is our website. If you go to the website, you can see a list of simulations and the data access, recipes on setting up paleoclimate simulations, version navigation, and some diagnostic plots as well. We have an email list listed here. Please considering subscribing to our email list to stay connected. Discuss CESM forum is a place to ask related questions. And please also considering joining our winter meetings and summer workshop. Quick summary, paleoclimate provides unique constraints on CESM and also provides these opportunities to improve CESM. Overall, CESM is among the best performing models in CMIP. And for this paleo test, this should really increase our confidence about using this in research in future projection. And the paleo working group contributes to CESM development on water isotope capability. And please stay connected with us. With that, I will stop here and happy to take questions.
At how CESM performs in deeper time simulations when paleogeography and ocean currents were a lot different than today?
Yeah, that's a great question. That's what we do as well. Thanks for the question, so I can talk about that. First thing is that major climate forcing is still CO2. So once you have the climate sensitivity more or less okay, so in terms of global climate, you will have an overall reasonable simulation of temperatures. The paleogeography makes some contributions, but it's overall secondary. And that's from scientific perspective. From technical perspective, it's really, really challenging to develop a deep time simulation. If you check out the slides from presentation from Sophia from a couple years ago, she has a nice illustration about all those detailed processes. So technically, it's challenging, and we hope to develop to similar notebooks on deep time application as well, but it takes time. Does that address your question?
Great talk, thank you. I was wondering how the isotope-enabled CSM has changed between like CSM1 and CSM3?
Thanks. The proposal is funded last year, so we just started. And I think the most important thing is that we have resources now to develop the model in a way that it is easier to maintain and for the future. So hopefully it will live in CSM main trunk and it will be carried over to the future versions. So that's from software engineering perspective. Scientifically, I don't think we have like major differences. So we basically follow the water cycle in CSM. So all the differences will be carried over as well. So the isotopic hydrological cycle follows closely to the regular water cycle.
How do you think about the high ECS and colder than expected LGM temperatures in CESM2 impacting other components of the model that you would want to interpret, like the sea ice formation or ocean circulation? Like, is that a big caveat to that, or how do you think about that?
Yeah, thanks for the question. I think ECS is important. So basically, it tells you that if you have a high ECS, your global climate will be warmer when you add in external forcing, and you will have less sea ice. Your response in hydrological cycle might be also strengthened as well. One caveat here is that ECS is a metric for equilibrium climate state, like LGM as well. If you look at transient climate, it may be different. If you look at transient climate response, actually, you don't see a major difference between many of the CESM versions. The transient climate response are all around 2 degrees C. So does that address your question? Yeah, thanks.
Super cool talk. I was wondering if there are any plans to do a new last millennium ensemble with CSM3?
Yeah, that's a great question. Last millennial is a long simulation, and based on our senior scientist Betty Otto-Blissner's work over many, many years, internal variability is very important as well. That means the best use might be you develop last millennial ensemble. And given the cost of the model, it's very challenging to do. But we are really like open-minded. We would like to collaborate with like university groups who are interested in last millennial. So if we can join forces together, I think it's achievable. So basically, short answer is limited by the computing resources, human resources. Right now, we don't have a clear plan about how to carry out that important suite of simulation. Any more questions?
Going off of one of the previous questions, do you know like why the ECS kind of changed to go really high and then back to lower?
Yeah, it's documented in my paper, but in general, I think the major thing is in cloud feedback. For all the versions, if you have a stronger cloud feedback, the ECS would be stronger. That's a general finding there. And in the case of CSM2, it's also true. So the cloud feedback is too strong. And specifically, what we found was some inconsistencies in the macrophysics, ice nucleation. So we need to improve those aspects. Those are also very challenging thing to parameterize in the model. So we made some improvements, and we were able to reduce cloud feedback. So ECS is reduced as well. Yeah, more details are in my paper.
If I stop enabled is CSM, I want, well, like, do you have any primary proxies that you compare the outputs from models with the like measurement, or do you use any available proxy data? Yours.
Yeah.
Score or like I score. Do you use like do you focus more or use any proxies from the tropics and many other regions?
Yeah, absolutely. So the major advantage of ICESM is you can take advantage of available proxies that include coral records in the tropics, like the ENSO variability I showed you. Many of them are from coral reconstructions. And we can also compare with foraminifer oxygen isotope in the tropics. And we can also compare the simulated value with DAR-18O in the speleosome records in the lower latitudes. So yes, we have a plan to use like modern day observation from satellite observation, from flight campaigns, and the paleoclimate records from ice core, ocean sediments, etc. So, but this should be a community effort. There's a lot of work need to be done on that.
Let's thank Jung one more time.
Thank you. Great talk.
And is Jesse here? Oh, yeah, he is. All right, great. Okay. Next, we're going to move on to the intro to the lab today. And today we're doing diagnostics. And so Jesse Nussbaumer who is a scientist and software engineer in the atmosphere model and predictability section, will introduce the lab.
Great. Thanks, Sophia. Oh, whoops. Sorry. On now? Yes. It's okay. Yeah. Thanks, Sophia. Thanks, John, for that talk. I always wish I was in paleoclimate. Don't tell the atmosphere people I said that. So I'm here to talk about diagnostics. That's the practical for today. Obviously, you guys have been running models, but it's really hard to look at models just from raw output. So our goal here is to turn all those numbers you produced into pictures and other numbers. So let's dive right in because I don't think we have. Oh, you guys have. So the lab goals. Actually, how many of you already know or work with Python, the programming language? I'm just curious. Okay, yeah. Sorry. We first made this lab when Python was just kind of coming into our community, so this might be a relatively easy lab for you all. So, but anyways, you're all going to learn what you already know, which is learning about Python. We're going to try to run Jupyter notebooks on our new on-demand system. You guys are kind of guinea pigs. This is the first time this on-demand system has really been rolled out. And obviously then we're going to learn tips about visualizing CSM model output, and then learn about specific diagnostic software developed here at NCAR. Cool. Yeah, I'll probably skip this slide because again, most of you use Python. I will say we're using Python a lot. All of the scripts you've actually been using, like create new case and case build and case setup, those are actually all Python scripts if you were to open them. But for this lab, we're going to use Python then with extra packages, which again, I'm guessing a lot of you are familiar with, NumPy, Xarray, Matplotlib, Cartipy. We also are going to bring in some new NCAR-specific packages like UXarray, which I'll talk about later. But essentially, we're going to learn how to use these and apply them to the CSM model output for all components. So, how many of you have used a Jupyter notebook before? Oh my gosh. Okay. Well, you might have a lot of free time today. I don't know. Yeah. So in case you don't know, Jupyter Notebook is a way to run Python, and it's a way to display it kind of as if it was in a journal article or some sort of page, and allows you to execute cells independently. So that way, if everything's working and then one thing doesn't work, you don't have to rerun the whole script. You just rerun that cell. We have a system here at NCAR on demand, which allows you to, through a browser, just open up a Jupyter notebook, really through a system called Jupyter Hub, onto our Sizzle machines. And for this lab, we're going to be using Casper. Casper is the machine for data analysis and visualization, as opposed to Derecho, which is our true HPC system. Cool. And I will say, on-demand can be used to run other services and other programs through the web browser. I also learned the hard way that you can also use it to kill your jobs. So if you want to do that and not log in, that's a way. So cool. So just really quick, because in the past, sometimes we have had issues with everyone not being able to get on. So just to go through this real quick, when you start the tutorial, you want to go to this page, but basically the diagnostics header beginning. You'll then do step one, which is basically where you git clone. You will open a terminal. You'll just git clone all of the notebooks that you'll use today. Then you'll go to this on-demand page. Did you guys end up trying it? Oh, awesome. Okay, great. So it might not be a problem. So yeah, just but if you haven't signed in, just go to on-demand. You're going to open a new Jupyter Hub session or Jupyter session and use a compute node. Do not use a login node. We will get angry emails if we all jump into a login node. Also, just as a heads up, occasionally on-demand will hold your request in the queue forever if you have another Jupyter session running. So just FYI in the lab, if you're trying to log in and you just see you're waiting forever, just come get one of us, and it probably just means you have a session sitting there already. Cool. I'm blazing through this quickly. So there are some packages here which are being developed. The big new one is Cupid. Cupid is an attempt to try to generate standard diagnostics automatically. In this lab, you're going to run it kind of offline because the idea that the model's already been run. You just want to run this. And we're also going to use only a subset because if you run all of Cupid, it can take a while. However, I would definitely recommend you checking it out. We also have the capability that if you run a CSM simulation, CSM will then automatically run Cupid right after it in the queue and generate plots, including for all components all at the same time, and put it all on a web page. So this has been a major focus here in CGD of our latest diagnostics. And it's not going to cover everything. It's going to cover a lot of just standard plots, think like lat-long maps and time series and things like that. But there are some specialty plots in there, and you can always add your own. The other thing, there's another example of, it's also in the land model, if you're going to do the land model diagnostics, is UX-array. So I'm sure most of you are familiar with X-array, which is a way to read in netcdf files. The problem is, if you're going to use the plotting functions for that, it assumes a structured grid. That means like lat-long. Most of our raw model output is no longer on lat-long grids. The spectral element dicore, if you notice, you're opening that CDF file, it's just one dimension encall, and it has like 40 bajillion elements to it. So UX-array is a way to read those files directly without having to do regridding. That being said, we also have examples of regridding, because you might need that situation. But this is kind of the direction we're moving. CESM will probably continue moving, and all climate models, essentially for various numerical reasons, are moving to unstructured grids. So the more familiarity you get with plotting and analyzing unstructured grids, the better you'll be. So also, another major diagnostics package we developed here is the CVDP, the Climate Variability Diagnostics Package. This has been around a long time, and it's very powerful at analyzing any sort of modes of variability. So, ENSO, the NAO, PNA, AO, the AAO, all the other O's, and also doing statistics on them, right? Like, is there a trend in your model? Is there, what does the time series look like? What's the spectrum look like? Everything like that. The one I always make mistakes, so I won't make a mistake this time. The one oscillation that is not in this package is the MJO. And that's because the MJO is too high frequency for this package to handle. We do have another package which is in development with NOAA, the MDTF, which has MJO-related variability. But yeah, just FYI, if you're doing MJO stuff, this is not going to help you. But anything else, it's good. And then finally, another package we're developing is the ADF, AMG Diagnostics Framework. Originally, this was atmosphere focused, so this would have your general plots, but then also specialty plots, particularly related to, like I think we had Wacom talks earlier today. So higher altitude stuff, QBO, tape recorder, things like that. However, it's expanded. It's actually now the land model has a version, the LDF, which does a bunch of specialty land analyses automatically. And we also allow ADF to now run under Cupid. So again, if you send off Cupid, you can tell Cupid also send off this ADF package and run it. There's a bunch of stuff, including an extra tutorial down here at the link. So again, if you all blaze through today's tutorial and want to do something else, you can do this one. So awesome. All right, that was really quick. Thank you all for listening. Happy to take any questions, and yeah, appreciate it. Cool. Oh, yes.
I have a question, but I don't know if anyone else cares.
Go for it. No one else raised their hand.
So your climate oscillation SEO code, do you think that it could also read in work input?
The CVDP. If it's in, that's a good. Yeah, that's a good question. I don't know the answer to that, but I can point you to who would know the answer to that. So yeah. Yeah. I don't. Okay. Yeah, I know. It was painful to give up. Yeah, we were told we didn't volunteer. So yeah. Well, awesome. I guess it's tutorial time. Yeah. Cool. Thanks all.
climate section. And so I'm going to tell you a little bit about land ice modeling in CSM, but also what we do, why we care about land ice, and the research that we do with it. I would like to acknowledge that everything I'm going to present here, of course, there's generalities and so on, but it couldn't be possible without a lot of collaborators here at NCAR, but also everywhere else around the world. In particular here at NCAR, Bill Lipscomb and Kate Calder, whom you've seen around this week already, and all of the collaborators from the Land Ice Working Group. Okay, so to put everybody on the same stage here, let's first define land ice. What do we mean by land ice? And what we mean is simply snow that falls on the ground that has time to accumulate enough to then compact and reach a certain density and accumulate enough such that it can start flowing under its own weight. And this is very different from sea ice, which you heard about earlier this week, which is frozen seawater. So during this presentation, I'm going to tell you a little bit about land ice and sea level, which is one of the reasons why we care a lot about land ice and CSM, among other things. I'm going to tell you a little bit about ice sheet dynamics, how it works, and how land ice is represented in CSM, and the research that we have done, some of the research we've done so far, and what we keep thinking about. So first, land ice and sea level. So when we talk about land ice, especially contemporary land ice, we refer primarily to those big two ice sheets, Greenland and Antarctica, and all of the smaller mountain glaciers around the world. Antarctica and Greenland, sometimes we don't necessarily realize, but they're really big. If you were to compare them to the United States, Greenland is a quarter of the size of the continental US, and Antarctica is 1.5 times the size of the continental US. And you have the Greenland in the northern hemisphere and Antarctica in the southern hemisphere, and combined, they could rise global sea level by about 200 feet, or about 60 to 65 meters. They're starting to lose more and more mass, and their current contribution for Greenland, for example, right now is about 270 gigatons a year. And to put this number in perspective, 360 gigatons a year is about 1 millimeter of sea level equivalent globally. So right now, this means that Greenland contributes to about 3/4 of a millimeter of sea level every year around the world. Greenland, it's not as much yet. It's about 150 gigatons a year, but it's picking up the pace. Outside of these two ice sheets, we have mountain glaciers. And if you account for all of the ice contained in those mountain glaciers, it represents about 0.4 meters of sea level equivalent. So it's way less than the two big ice sheets that we just talked about. However, right now, the contribution to sea level is about 230 gigatons a year, which is very similar, close to what the Greenland ice sheet contributes to. But they're much smaller, so their water reservoir is not as big, and they're very sensitive to climate change, and they're spread out all around the world. And of course, they contribute to sea level, but they have more importance for us human beings because they're like it is the case in Colorado. This is our water source, fresh water source. So the more they retreat, the less water we get. And here, I've put here a comparison of what happened to the Mer de Glace, which is the biggest glacier in France, in Chamonix, and you can see where it was in 1900, its elevation in 2019. The ice here, you can see that there's about 100 meters of ice that just is gone, and now you need a ladder to go down to the base of the ice, to the top of the ice, like when you didn't need to 100 years ago. There's one way also that we differentiate between ice sheets and other land ice masses. For example, here, when we talk about Iceland, we refer to this as an ice cap. And these ice caps are between like 20,000 to 50,000 square kilometers, and everything that is bigger than that, we call it an ice sheet. Okay, so of course, when you think about sea level, you're thinking about those ice sheets that they lose their ice and then it goes into the ocean. But of course, there are other processes that contribute to sea level. And you have thermal expansion, which is when you warm the ocean, it expands and contribute to sea level as well. And if you look at the numbers for the 20th century, the thermal expansion was equivalent to the contribution to sea level, to thermal expansion was very equivalent to the contribution of the Greenland ice sheet. And at that time, the Antarctic ice sheet, was pretty much in equilibrium with its climate and did not contribute too much. And the major part of sea level contribution came from the glaciers, mountain glaciers around the world. This picture has changed in the 21st century, during which the thermal expansion contribution has now is multiplied by 4. Glaciers still contribute about the same amount, but the Greenland ice sheet contributes 3 times as much, and Antarctica now is starting to contribute more. It's picking up the pace to catch up to contribute almost as much as glaciers and to catch up with the Greenland ice sheet. Okay. When we think about sea level, typically we give numbers in a sense of global sea level equivalent. So you measure it around the world and you say, okay, equally, this is how much sea level you would get. But sea level is really a regional concept, and you have regional sea level variation all around the world. And since the 1993, we have now satellite altimetry that can give us a better representation on the variation of sea level around the world. And this is a picture created by satellite altimetry. This is an average between 1993 and 2019. And in red, the redder you are in this picture, the higher the sea level, and in blue, the lowest sea level. So you can see here in the Southern Ocean, you have sea level that is way lower compared to the rest of the world, and this is due to some ocean circulation changes and other processes. So this variation in regional sea level come from very different factors. You have land subsidence when the land starts to go down, but due to glacial, and you also have glacial rebounds. So this glacial rebounds is that the people don't necessarily think about it too much, is that when you have a big load of ice that is on land, well, it's going to compress the mantle of the Earth, and then the mantle is going to bulge elsewhere. And as you remove this ice, well, the mantle is going to rebound, and all of this causes sea level change. On top of this, ironically, when you lose ice mass, you actually have a sea level fall around this ice mass loss because you have less self-gravity attracting the water towards it. So if you were to use a solid Earth model, which is a model that would capture this change in the mantle variation, then you would see that if you were to get rid of a lot of the Antarctic ice sheet ice mass over here, you would actually have a lot of sea level sink around Antarctica and a lot of sea level rise anywhere else around the world except somewhere, there's a label in the middle of Asia, Eurasia here, they get a rest. But in Greenland, it's a bit the opposite. You have sea level fall around Greenland, and then the Southern Ocean, the Southern Hemisphere is going to catch up this rise of sea level. So right now, if you were to live in Florida, we would hope that the Greenland ice sheet would melt faster than the Antarctic ice sheet. Otherwise, you'd end up with a beachfront property very quickly. So if you look at the sea level signal that you can get by proxy, by paleo proxy data, you would get a figure here that shows a coevolution between carbon dioxide concentration, global temperature, and sea level. And you can see that over the past 400,000 years. And the story that this tells is that those 3 components co-evolved together with very complicated physics. But at the time, before humans were there, the primary changes, there's a lot of orbital changes where the Earth and the Sun were rotating and were aligned with each other. And this was enough to create all of this variability. And you can see there's this 100,000-year cycle in which those three co-evolve. And if you look at the last interglacial, which is about 125,000 years ago, you had a peak. There's a time when sea level dropped by over 400 feet in the course of several tens of thousands of years. And these information are very crucial for us because they help us try to understand what can happen in the future. Now, if you zoom in into the 1900s here, you have this huge peak in carbon dioxide here, and I guess you can guess what created this. Thank you, us. So we are here, and we weren't here before, and this is in the past 400,000 years. This is the only time when you see a peak of CO2 that goes about 300 parts per million. So now this signal is driving the rise in sea level that we see today. And so, like I said, this huge variation in sea level, we can try to learn from them to start to understand what could happen in the future. And if you look at the last interglacial, like I was mentioning, 125,000 years ago, the climate was a little bit warmer than it is today by about 1-2 degrees. So we're getting there, but at that time the carbon dioxide concentration was about 280 parts per million ppm. So the CO2 was not as high, but the change in the temperature was pretty equivalent. And if you look at the proxy data, the sea level was about 6 to 9 meters higher than it is today in comparison. 2 to 4 meters was coming from, we think, was coming from Greenland, and the rest was coming from Antarctica, and we're still trying to understand the processes that led Antarctica to lose that much mass during this time. So this is a figure that shows the retreat of the Greenland ice sheet, and that was a paper that Bediotto Blissner published in 2006. And if you go back a little bit further back, 3 million years ago, during the Pliocene era, this is a time during which the carbon dioxide concentration was very similar to today, and the warming compared to the pre-industrial level was about 2 to 3 degrees warmer. So if you think history is going to repeat itself, or things being equal, this is where we're headed, given our current state of emission. But at that time, the global sea level, we estimate that it was 5 to 20 meters higher than it is today. And I would like to draw your attention that this is a problem that we have when we do paleo proxy data. Like the uncertainty is huge. 5 to 20 meters. That's not small, but that we have to work with. But it gives us an estimate of like what to look for. And during this, if we think that the change was more on the higher end, then up to 7 meters of sea level was coming from Greenland, and you can see the ice that retreated here. And about 5 meters was coming from Antarctica, most likely coming from the West Antarctic ice sheet that is, I'm trying to circle around here, that is very sensitive to changing climate. So now, today we have the IPCC report and AR6 that we're trying to get a sense of our climate and where we're headed. I'm sorry, I forget acronyms, so I hope you're all familiar with IPCC and you'll give me a break. Intercomparison Panel for Climate Change, you got it? Yeah, something like that, close enough? Okay, thanks. And so in this report, they do study about the project global mean sea level rise that is to be expected, and they take many things into account. And the report that was written for AR6 was indicating that it is virtually certain that the Greenland ice sheet and very likely that the Antarctic ice sheet will continue to lose mass in the future. And they also drew a lot of I'm missing my word here. They cautioned us also in a sense that these estimations do not include some processes that we're still trying to better understand and figure out. And this is part of the science that we here also at NCAR are working on. And those processes are, you might have heard of it, the Marianas Cliff instability. It made the news, and it's a process that has been very, that didn't draw the community together because only one model really is capable of representing it correctly, and no other model is really capable of doing so. But more importantly, the sub-ice shelf melting under in ice shelf cavities is a big uncertainty. But right now, what this story tells us is that by the end of 2150, under low emission scenarios, which is represented here in this green and black curve, we're going to get between 28 to 55 centimeters of sea level rise equivalent. And if we go towards a higher end scenario when it's very strong warming scenario that we let our model continue evaluating these processes, and we get up to 1 meter of sea level equivalent by 2150. Okay. So I would like to tell you a little bit about ice sheet dynamics and how it's represented in the community ice sheet model, which is an ice sheet model that we use in CESM, the community Earth system model. So how do glaciers move? So I told you what we call land ice. You need gravity, and ice flows under its own weight. That's great. But then you have this ice that also is subject to internal deformation by shearing. So when you have when you have a piece of land ice flowing on a bed, and the bed here is represented by this word lithosphere, for any other word, from lack of other words, you have this bed provides some a counter stress that slows down the ice sheet, and so you have the internal shearing, and then you have gravity. And those three components have to coexist and will make the land ice flow. If you think about land ice, and if it's a little bit counterintuitive to you, but think about honey. We consider land ice to be a very viscous fluid. Even though it's ice, it's very viscous. And you get a good approximation of what it does. When you have honey, it's very cold outside. You leave it outside in the winter, and you try to squeeze your bottle. It takes a while to flow down, even if it's completely vertical. Do the same in the summer, well, you get it faster. Ice sheets are pretty much the same. So there's a given for the ice sheet. The velocity of the ice sheet is always going to be the lowest at the bed and always the fastest at the surface. And when the ice sheet, in the interior of an ice sheet, when the ice is flowing, sliding slowly, you have a strong vertical shear that makes the surface of the ice flow faster than the bottom. As you move towards the terminus of the glacier, eventually, you have basal as the ice sheet slides. It will create some basal melting, and then the till at the bed will get well lubricated, and and the ice sheet is going to start to slide. And at that time, when the ice sheet starts to slide, then the velocity at the base of the ice sheet is going to pick up and can almost equal the velocity at the top of the ice sheet. So the way you can get lubrication at the bed, you can get in different fashions. So you can, by friction, as the ice advances, it can melt it. Or in the case of Greenland, you can have those features that are called moulins. So you have surface melt on top of the ice sheet, and then eventually, with kinetic energy, it's going to dig a hole through the ice. That water is going to flow directly under the ice and lubricate the bed. You also have the case of marine intermediate glaciers, and so those glaciers end up in the ocean, whether it has a floating ice component with an ice shelf, or it's a cliff termini glacier without an ice shelf. They have a direct access to the ocean, and so the ocean can go under the bed and lubricate that bed to make the ice slide faster. So what you're looking at here is a figure of Greenland velocity, and the blue scale shows you slow-moving ice, and the red shows you fast-moving ice. And this band that you can see in the look like a separator is called the ice divide. This is where the ice slows the slowest. no, I'm losing my words. Flows, so slowest, thank you. And when you do modeling, eventually, you enter all of your equation into a computer, and then you want a solution. And ideally, you would like a model that is fast and accurate. Typically, these two don't go well together. And it depends on your tolerance. It depends on what you're after. But in the ice sheet world, you can, when you have your ice that is frozen at the bed and the ice doesn't flow too fast, then you can model this using what is called the shallow ice approximation, which is valid when the ice flows up to tens of meters a year. And the wonderful thing about this approximation, it has a mathematical and analytical solution, so you can compare it directly. You don't necessarily need, you don't necessarily need data. You can just compare it to this mathematical form. And it is computationally very cheap, even if you run it in serial. On the other hand, when your ice flows fast, and here this is pointing to a particular place in Greenland, it's the Jakobshavn-Isbrae glacier, the fastest glacier in Greenland, then the shallow ice approximation is no longer valid. So you're not going to get great representation of your model. And this is when you need to switch to the shallow shelf approximation that is better suited when your ice is actually sliding. This is valid for when the ice flows from 100 meters to several kilometers a year. It's still computationally cheap, and it's very valid when you have water at the bed. In general, you would like to be able to have a good representation in any circumstances. And this is when you use what is called the Stokes equation, very similar to the Navier-Stokes equation that you might have heard in lectures earlier this week already. Or what we call higher order approximation. This is when we do simple assumption about the Stokes equation that does not break all of the Stokes approximation assumption. So they're very good at representing any ice flows, but you pay the price of computational of being computationally more heavy. In CESM, right now, the ice sheet model that we have uses what is called a depth-integrated vertical approximation. So you are solving all of the spectrum of velocities, but over a single column, you take the average velocity and then you solve for the equation, and it is still cheaper than solving for all of the velocity layers at once, and it still gives you a good accuracy everywhere in the ice sheet. And this is the solver that I used that we use to represent the velocity as well in our model. That matches very well this observation. Okay, so we know how the ice is flowing now, and now let's talk a little bit about how ice sheets gain and lose mass. So here, in this figure, you have your ice sheet that sits on a hard bed, and you have snow that falls on the ice sheet and eventually compacts and it grows. Then, of course, your ice flow, but in the meantime, you have some climatic condition that act on it and make it react to it and make the ice react to it. So one of them is, as indicated in the picture earlier, surface melt. And this surface melt eventually will eat up the ice and will be dumped outside of the ice and does not necessarily refreeze. You have those floating ice shelves here, which is when the ice is lifted up from the ground and start to float, and the location where it happened is called the grounding line. And then these ice shelves can then be melted from below by warmer ocean waters. Eventually, these ice shelves also could break off to become icebergs. And when you account for all of this change in mass loss, if you sum them all together, this is what we call the mass balance. And when the mass that comes in is greater than the mass that comes out, you have sea level sink. And when the opposite happens, you have sea level rise. Okay. Now, in order to understand the processes that are very important for the ice sheet that you're modeling, it is very important to to familiarize yourself with the bed topography that they sit on. What you're looking at here is a picture of the bedrock elevation of the Greenland ice sheet, and you can see that it varies. Whatever is not blue is bedrock that lives above sea level, and whatever is blue is at sea level or below. And it doesn't necessarily mean that you already have ocean water there, especially in the middle of Greenland, but this is a potential area where where ocean water could come in if there's a pathway for it. On top here, what you're looking at here is the Greenland ice thickness that sits on this bedrock, and you can see that it varies between tens of meters to up to 3.5 kilometers. What this picture shows you, there's no strong, very light white around it, and that's because the Greenland ice sheet has very few ice shelves compared to Antarctica, it has almost none. For this reason, and when you look at the bed topography here, and if you were to overlay the ice, it would sit on those very high, steep topography on the east and south of Greenland, and those shallower topography on the north and the west. And for this reason, the ocean doesn't have as strong of an impact on Greenland compared to surface runoff or iceberg calving. Now, if we go to Antarctica, the picture is a little bit different in the sense that this is, again, the bedrock elevation and the ice thickness that is on top of Antarctica. And you can see here, Antarctica, its bed topography, a lot of it lies below sea level. When you look at the ice thickness of the ice sheet, you can see these big white areas. Those are two big ice shelves. So you have the runny ice shelves in the north, they're all in the north, but on the top of the figure, and the Ross ice shelf at the bottom part of the figure. And to give you a sense of scale, the size of these ice shelves is as big as France. You also have a little bit of floating ice in these areas, the Amundsen Sea embayment, and this means that the ocean, warm water ocean, can penetrate under these ice shelves and start to melt them from below. And because Antarctica is a desert, there's very little snow that falls on it, especially in the interior. You have a bunch on the coast, but very little in the interior. And it's very cold. It's much colder, even during the summertime for Antarctica. There's very little surface melt in Antarctica. And so whatever falls into Antarctica is balanced by either iceberg calving or ice shelf melting. Now, I'm talking about warm water penetration in Antarctica. And like I just said, much of the Antarctic ice sheet sits on a bed that's below sea level. And you have these two areas, the Amundsen Sea embayment with the Thwaites and Panamanian glaciers. And you might have heard about them in the news, like the Doomsday Glacier and all that jazz. And as I mentioned, this is a very, the Western Antarctic ice sheet over here is a very sensitive area because most of its bed lies below sea level. So once you remove an ice shelf, so ice shelves are floating ice and they already contribute to sea level. So whenever you get rid of them, sea level doesn't rise. It's already there. However, those ice shelves sometimes are very important because they provide back stress to the ice that is flowing with them. So it slows them down a little bit. If you get rid of them, then the ice has all of this space to flow in and then contribute to sea level. And the Western Antarctic ice sheet is a little bit particular here, not only because you can have warm water from the ocean that can potentially go up the continental slope and then make it under the cavities here to melt the ice at the bed. But if you look at the color scale here, I'm going to get this right. Okay, it goes from light blue to darker blue. And if you look at the scale, it means that you go from shallower bathymetry to very deep bathymetry. And it means that the bed, as the ice sheet flows forward, the bed is going up. And this is called a reverse sloping seabed in our jargon. and it's subject to what we call the marine ice sheet instability. So you might have heard this term in the news as well, and I would like to take a moment here to set something straight. We use some words sometimes without forgetting where they're coming from and what the meaning of it is. And this marine ice sheet instability concept is a mathematical concept that was developed in the early, in like around 2010, like slightly a couple of years before 2010. And it says, for marine Termini glacier, so you need to have your ice sheet, your ice that ends in the ocean. If your ice sheet is unbuttressed, so there is no friction from the wall that can slow it down, and if it sits on a reverse sloping slope, then it's going to retreat without being stoppable. And if you look at the configuration in the Amundsen Sea embayment for Thwaites and Barron Glacier, the condition is set for this to be satisfied. However, there's a lot of buttressing happening there, or some. So when people use this marine ice sheet instability jargon, before they can use it, they need to make the case that the buttressing does not exist or is very small. And typically, that's not the case. So whether it's a sensitive area, yes, it is, because as you melt the ice here, then you expose even the ice is thicker as you go down that reverse slope, and so you expose even more ice subject to melt. And so it's going to entrain this ice to retreat even more rapidly. Is it the marine ice sheet instability? Not necessarily. And so let's be careful in how you use terminology, even in our papers. And as you grow in your career, that's a message I want you to get from, at least from this slide. Okay, now what you might care a little bit the most about, ice sheets in the community Earth system model. So as I mentioned before, the ice sheet that we use is called the community ice sheet model. And before CSM was called CSM, it was called CCSM, the Community Climate System Model. And before the ice sheet were introduced, Peter Gent was the chief scientist, and my supervisor, Bill Lipscomb, who was working on ice sheet model, came to him and said, hey, what about ice sheet in CCSM? And Peter pretty much said, cool, good idea. And this plus biogeochemistry and many other things where you could finally look at the carbon cycle led to one, and among other reasons, led to the change from CCSM to CESM, where you can do Earth system modeling now. One thing to know is that ice sheet models, they're annoying for Earth system models. And the reason for this is that back, earlier in the day with CCSM, you had the population model, you had the land, and you had the atmosphere and the sea ice and the ocean. They like each other pretty much. They're on the same grid, or at least on the same spatial resolution. And POP, the ocean model at the time, didn't have any varying boundaries, so they were fixed. So everything was fine. But an ice sheet, you can assume fixed boundaries with an ice sheet because it retracts and it grows. So all of a sudden, you are introducing a changing grid in a system that never had this concept before. What do you do? That's annoying. We worked around it. It's working. And one of the reasons is that the ice sheet is very well intertwined with the land model. So at first, when you build a new capability, you go slowly. And what we did first, we put the ice sheet there. And the difference between having an ice sheet component as opposed to an ice sheet representation is that we can resolve it at a much finer scale. So the resolution of the ice sheet model is about it's a uniform grid, and it's 4 kilometers. So it's way higher resolution than any other component in CSM. And even though at first it was not dynamically evolving within CSM, what we did is that we had the land model compute the surface mass balance, and then downscale it on the ice sheet grid, which was finer than the CLM grid before then. And this remapping was done by the coupler, and then this surface mass balance term could be now better distributed over the ice sheet. 2 minutes. Huh. Okay. So, in CSM2, we went for one-way coupling or no evolving ice sheet to being able to evolve the ice sheet in CSM. And so I'm going to go very fast. And in CSM3, pretty much everything remains a little bit the same as CSM2 when you have the exchange between the evolving ice sheet and the land. That was said. And now what's new is that we have now the full interaction between the ocean and the ice sheet. So right now, the ocean receives the solid and liquid fluxes from the ice sheet, and the capability is there for the ice sheet to receive melt rates from the ocean. While we don't do interactive ice sheet in CSM3 right now, the capability is there. You can do it. We just need to validate it. Well, I think I need to skip through the ice sheet initialization then. But pretty much this is to say that in order to initialize the ice sheet, even whether it's a standalone or a component of the CSM model, you need a few boundary conditions. So you need the bed, you need the ice thickness, you need surface mass balance and temperature, you need geothermal heat flux at the base of the ice, and in the case we have ice shelves, you need ocean thermal forcing, which will derive the melt rates for your ice sheet. And then you take all of this, and one thing that we don't know in ice sheet physics is what's happening at the bed and the resistance at the bed. And the spin-up process is pretty much to give us a map of this basal coefficient, which we don't know anything about. Because you have the conservation of mass and momentum, it's a closed system, you can derive a value for this component, and this is what you do with this inversion. You run it for 10 to 20,000 years, it takes like a day to do this, and then you can do your ice sheet simulation. When you do a spin-up like this, typically your ice sheet ends up in full balance with your climate. It means that when you start your ice sheet is very, very happy, is very well balanced, and you don't see a strong change originally. And we know by now that those ice sheets are not imbalanced. And if you look at this figure here, this is a change in ice thickness for the past 15 years or so. And you can see that in this emergency embayment here, you have a strong thinning of the ice, which if you do a traditional spin-up method, you will not capture. So what you can do instead is take the same principle of spinning up for your ice sheet, include this map in a sense of data assimilation, and then get these exact rates of change in your ice sheet originally. If you run this model forward for about 1,000 years, the entire emergency embayment collapses without any additional forcing or changes. So this is a Greenland ice sheet in CSM3. What you're looking at here is the surface mass balance. It's fresh out of the oven, meaning that this is what we're using right now in the development of CSM3. And once we release it, you're going to get something similar to this for the surface mass balance that is used for the pre-industrial control experiments. And the goal with CSM3 is to have the Greenland ice sheet being turned on by default as opposed to being an option. Here we're comparing, so this is CSM3, the surface mass balance. We compare it to what it's called RACMO, which is a regional climate model that has a resolution of 5 to 10 kilometers as opposed to way coarser than CSM3. And you can see that overall there's a very good agreement in surface mass balance in CSM compared to those regional climate models. Those differences typically are due to like the coarser grid of the land model, which is harder to resolve. And what you see in red, those are ablation zones where you're supposed to lose mass. You can see that we do not have as much ablation zone in CSM3 right now compared to RACMO, but something to keep in mind is that RACMO here is a contemporary surface mass balance product, while we are still in 1850 for the pre-industrial. And if you were to use this surface mass balance product and use it to spin up your ice sheet forward, this is the ice thickness you would get in return. And this is the thickness in CSM3 and compared to observation. And overall, it agrees very well. You have a little bit of spurious advances on the outskirts of Greenland, but this is also due to the coarse resolution surface mass balance that we get from the land model. Okay, so recent and ongoing research, if I skip through this quickly, I can tell you that in CSM2, we ran the fully coupled system with evolving ice sheet by ramping up the climate to 4 times CO2 to see what would happen with the Greenland ice sheet. And no surprise there, it would rapidly contract, retreat, and this was, you can see here's the evolution of the ice thickness from the contemporary to the end of the century, where the ablation zone really increased by a lot, and that was just after 100 years. We used CSM also to do paleo ice sheet simulation, and this is an example of the last interglacial maximum, where at the time the Greenland ice sheet shrunk from being at about 8.3 meters sea level equivalent down to 4.2 meters sea level equivalent. And this study was done here with Alia Summers. And what triggered this strong retreat was a change in vegetation, which provided local albedo feedbacks and enhanced the retreat of the Greenland ice sheet. If you were to not include this feedback, then the loss of ice would be half of that. So we also do other study with the Greenland ice sheet, with calving. Just a second here to also tell you that we're using an ice sheet model to do mountain glacier modeling as well. And this way, in this experiment, we're modeling all the alpine glacier, 4,000 of them at once, on a grid resolution of about 100 meters, as opposed to 4 kilometers. And in this experiment, we pretty much ran the model forward for 100 years and experienced that under the same climate condition as we have today, all the glaciers in the Alps would lose about 60% of their volume. Okay. So this is what we plan on doing for future CESM development. We want to improve ice shelf cavity circulation to get a better representation of melt rates under them. We want to improve our glacier projection for other regions outside of the Alps, but we also want to include a solid earth and sea level capability to better capture these changes. This, of course, translates for CESM as well. We're also going to contribute to ISMIP 7. It's in the work right now. And I will almost stop there. If you have any questions about land ice, please contact me or whoever is on this list. You'll have access to the slides. And please feel free to join our community. It's friendly. I needed it all. And whether you're an ice sheet modeler or not, or if you're just curious, please join us. And last but not least, just a reminder that when you do modeling, there's perspective on what you do and your research question, based on your perspective, could be very different of what you expect. So let's keep this in mind. Thank you.
Thank you. Unfortunately, we don't have time for questions, but please email Gunter if you have questions and potentially meet for lunch tomorrow.
Yes.
We're going to go ahead and move to our next lecture, a shorter specialized lecture. Clara Desser is a senior scientist in the climate analysis section, and she will be talking about climate variability.
Thank you, guys. Good luck.
Really nice to see everyone here. This is one of my favorite talks to give because all of you are my hope for climate science moving forward. So it's so nice to see everyone. I thought because super El Nino is such a prevalent term right now in the media that I would devote this next 20 minutes to just covering the status of the El Nino, the latest forecasts, which were just released this morning. So I updated a few slides, so it's truly hot off the press. And then to talk about how El Nino might affect our climate or weather and climate over the US this coming winter. So that's what's on the agenda. Yeah, so I'm taking a lot of my slides at the beginning from very nice updates that are released monthly. Typically, yeah, at the end of the month, but this one was, so this is from 29th of June, but I've updated some of the forecast slides from literally this morning. Okay, so the current status of sea surface temperatures in the tropical Pacific, the heart of the El Nino-ENSO region. And this is, again, taken from the CPC website. So you can see that very pronounced red area along the equator in the Pacific Ocean. Sea surface temperature is above normal, roughly between 1 and 2 degrees already for the month of June. It hasn't changed that much in the last month. It's maybe increased by a couple of tenths of a degree, but at this point, this is roughly what it looks like as of today. And then there are these typical indices. I'm sure most people are very familiar. So along the coast of Peru and Ecuador there, that's this region called Nino 1-2 because those are the ship tracks that were recording the data. So you can see the graph on the right. That's over the last year or 2 years. So in this region along the coast, we came out of cold conditions around January of this year. And now the coastal regions are exceeding 2.5 degrees, which is very pronounced. Then the typical metric for ENSO is this region in the central equatorial Pacific called Nino 3-4 because of ship tracks. So 2 things to point out. The time at which the warming actually started to appear in the central Pacific here was quite a bit delayed from what was on the coast. So we already knew a strong El Nino was already happening this spring along the coast, and now, as is typical for many of the strong El Nino events, it's developed into a basin-wide event. And the amplitude in this region is 1.2 degrees C, and that remains unchanged from this morning's update. And that's a roughly 2 standard deviation departure. So we're already at, a very pronounced event if we're already, at the 2 standard deviation level. So we can look a little bit at the atmospheric and subsurface ocean conditions that are accompanying these sea surface temperature anomalies. So here is the picture, the graph for outgoing long-wave radiation measured by satellites. That's a measure of the cloud top height, and it's roughly inversely proportional to precipitation. So deep thunderstorms, cold tops, producing a lot of rain. So I've just marked here in blue, those are the wetter than average regions. And then you see the red areas, red and orange, those would be drier than normal for this past month. And that is, again, a very typical pattern that occurs with El Nino events. And then we can look at the lower tropospheric winds, very similar to the surface winds. It's hard to see the arrows, but I've just put in that schematic arrow. So there are anomalies from the west. So this is a weakening of the trade winds, which are usually from the east. And their magnitudes are quite strong. So again, these are very typical atmosphere-ocean patterns that we've seen for past El Nino events. And then finally, we can look beneath the surface, which is crucial for the future progression or evolution of this event. So this is the figure that shows along the equator. So we're just looking at longitude on the x-axis, and then depth down in the ocean from the sea surface down to 300 meters. And I've just marked the rough magnitude of what we're seeing at depth. There's a 6-degree C anomaly, or a large heat content reservoir that is now continuing to be tapped. And that will really, that's what is driving the growth of this event. So as long as we see a lot of heat down beneath, in the thermocline beneath the sea surface, it's very likely that this event could continue to tap that heat and continue to grow. So these are all very consistent with theory and sort of these schematic representations based on theory of El Nino. And we're really seeing all of the signatures. We're seeing the sea surface temperatures warming on the equator across the basin. We're seeing the convection, the precipitation shifting eastward. We're seeing the westerly wind anomalies, a weakening of the trade winds, and then we're seeing this subsurface heat reservoir. So very, it's just a very typical event, maybe not so typical in its amplitude, but in terms of how the ocean and atmosphere are engaged, that is very typical. Okay, so let's go on to the forecasts. And these are the slides I updated just a few hours ago. And I'm glad I did, because it's even more dramatic than the previous month's forecast, which I think I showed Adam, or wherever he is, yesterday. Okay, so these are forecasts that are put out, in this case by NOAA, but there are other modeling centers like the European Center and others that do similar kinds of forecasts. And I would say I've looked at them all, the roughly similar results. So we can just focus on these, the NOAA NCEP CPC results. So they have a forecast system. It's a coupled model, a little bit like CESM. And then you supply the observed conditions, in this case, initialized from the observations, subsurface ocean temperatures, atmospheric conditions, everything that we can measure at this time. And then you let that model integrate forward with the equations, the physical equations that govern ocean-atmosphere coupling, thermodynamic and dynamical coupling. So they run a lot of forecasts, and I put that diamond there as they run the forecasts, I think, for almost every day. And this window here is for initializations about a month ago, roughly. So you can see the various trajectories of the different forecasts. There's some, of course, spread in the forecasts. This is a chaotic system. You expect that, there could be slight deviations depending on what kind of weather happens to occur during the forecast period. But all of them do show this very similar progression with an expected peak of the equatorial sea surface temperature anomalies in this Niño 3-4 region in November. And the amplitude of that peak is really big. So I've just marked the 2 and 3 degrees Celsius thresholds here. And you can see that now 50%, well, it's kind of centered on 3 degrees. Last month, it was centered on roughly 2 degrees. So that reservoir of warm water and a recent westerly wind burst, I think, is maybe behind why now these forecasts are even more calling for an even stronger event compared to a month ago. So how strong is 3 degrees? So again, I'm relying all on this NOAA website. So they have these categories that are in 0.5 degree C increments. So a weak El Nino is deemed to happen when this Niño 3-4 index is between 0.5 and 1 degree Celsius. And then we have the moderate category, the strong, and the very strong. They never use the word super. That is from the media. Okay. So very strong is when this index exceeds 2 degrees Celsius. So we're well above that with these forecasts. We are now at 3, so I wouldn't be surprised if they have to introduce an extreme El Nino category. So this is definitely going to be, or likely to be, a very strong event, and probably stronger than most events in the past. And I will show you a graph of that in a moment. So the other thing that they do is to put out the probabilities of the strength of this Niño 3-4 index as a function of season. So this is how they graph that information. So they take all of the initialized forecasts. I think they run 40 at a time. They're only showing a subset here in these thin curves. But anyway, they take all 40, and then they just, for each of these seasons along the horizontal axis, they just count up how many of the forecasts are within these different thresholds or different categories of ENSO strength. So I've just marked here. Yeah, so my percentages there are the probability of having a very strong event. So Niño 3-4 anomalies exceeding 2 degrees C. And you can see those percentages, 81%, for example, for October, November, December, so early this coming winter. And then it tails off by the time we get to December, January, February, which is the time when climate impacts most often happen over the US. It's down to 50-50, or 50%, very strong. But the other 50% is still in the strong category. So it's 100% chance probability of El Nino, and then about 50-50 whether it is in the strong category or the very strong category. So this is a very certain forecast. And of course, the skill of this model has been assessed using hindcasts, and I think we have quite a bit of confidence in the skill. Okay, so now I'll move on just to show you the time series of this Niño 3-4 region, sea surface temperature anomalies in this region back to 1950. And I've again put those thresholds that are for the strong events, 1.5 degrees C, and then the 2 degrees, the very strong. And so if you look at that 2 degrees C, very strong threshold, there's been around 6 events since 1950. So these forecasts indicate, around 3 degrees, give plus or minus maybe 0.5 degree or 1/4. So if that forecast verifies, it will actually exceed, for this time period, any of these previous events. But, we'll wait to see what actually happens. Okay, so now we want to move to climate impacts. And that's kind of another, it's just another topic. And I'll show you why. We have to distinguish it from the actual conditions. So these schematics of the canonical El Nino impacts, these are really powerful ways to communicate, what are the expected impacts on precipitation and air temperature over North America, in this case for the winter, December, January, February season, and then how the jet stream is altered because of the convection that's happening in the tropical Pacific. So this is what one might expect to see in this coming winter, especially given that we have a strong El Nino in the pipeline. But that is not guaranteed. And I'm just going to show you something that I think is really important to show. So this is a beautiful blog that Nat Johnson and Michel Lheureux at NOAA CPC put out. An ENSO blog. I highly recommend looking at the posts. This was from a few years ago, before the 2023-24 El Nino. So that's why that El Nino event is not included. But they have these maps of precipitation anomalies, so relative to a climatology, for this December, January, February winter season, where they just show them in descending order of the strength of the Nino 3-4 index. So how strong the El Nino was in each of these winters. So the strongest, 1982-83 on the upper left there. You see a lot enhanced rainfall all along the West Coast, and then in the Southeast US, and then drying out in the upper Northeast portion of the country. And then you just, take a look at all these maps. They don't all look the same, and they don't all look like those canonical impacts. Even though all of these events in the top row are in the very strong category, and these ones in the bottom row are in that moderate category, or maybe they're still in the strong category. Maybe I'm mixed up a little bit. So we can just look a little bit. For example, the two biggest events since 1950, you cannot count on what the impacts will be along the West Coast. We always hear a lot about California rainfall, especially Southern California rainfall, being impacted by El Nino, having more flooding. But that doesn't always happen, even with these very strong events. Another example, look down here at the Southeast US. Again, two comparable strength events, opposite signed anomalies. And then finally, I picked out, this north-south dipole pattern that is opposite between the 2015-16 event and the 72-73. So this is all to say that El Nino will tip the odds of wetter or drier conditions according to that canonical map of the canonical impacts, but it's not guaranteed by any means. And I think we forget this, or the media forgets to communicate this. Okay, so in a nutshell, what we are facing this winter, we have a highly certain forecast of a, I would say now, maybe exceptionally strong El Nino. But it doesn't guarantee that we will actually experience the canonical impacts. So why? Why did those maps look so different from one event to another? So I've just put down maybe three broad brush categories of reasons. The first is that these teleconnections that El Nino drives, these changes in the jet stream and the circulation over North America, that is always going to be superimposed on just some, random chance anomaly of the jet stream. It has a lot of chaotic behavior, obviously. So that's, I think, a primary reason why those individual maps look different, because you always have that superposition between the El Nino-driven impact or teleconnection and a pattern that is just mostly from intrinsic variability in the atmosphere. Secondly, these canonical impacts, this map on the lower right, actually that map is quite uncertain. I'd done some work some years ago, and because we don't have all that many El Nino events to composite to actually quantify with high certainty what the magnitude of those impacts are. So that's another thing to keep in mind. And then the final thing, which I will speak a little bit more about before I close, is another really important thing for everyone in this room, because you are all young, and will continue to experience climate change going forward. So there's now, I think, quite compelling evidence that background climate change is altering the teleconnections that are driven by El Nino. So even if the El Nino events themselves don't change character with climate change, they might intensify, but even if they don't, the teleconnections will not be the same as the historical data might indicate. So I'm going to show you an example from a paper. These earlier papers, they speak to these first 2 points if you're interested in reading more about that. And then the paper that is, in, I think, the January issue this year of Journal of Climate, that was a study that we did here at NCAR. Other people have done it with other climate atmospheric models and get similar results. But I'll just show you the results that we got. So what we did was we looked at the 2023-24 El Nino. That's the last big El Nino that occurred. And here are the sea surface temperature anomalies in this December, January, February for that winter. And the Nino 3.4 index was 1.9 degrees C above normal. So it almost reached that very strong threshold category. Okay, so then we prescribed this pattern of sea surface temperature anomalies to the atmospheric model. In our case, we used CAM6 at 1 degree resolution, and we ran that experiment with prescribed sea surface temperatures. We ran it 50 times with slightly different initial conditions. And the reason for doing that is to just minimize, when you take the average over all the runs, any intrinsic atmospheric variability that might mask the El Nino-driven teleconnection, the point that I was making just a couple of slides ago. So this is what the model produced, and those dots mean that there's no significant response. And I have studied El Nino since my PhD, a very, very long time ago, before you were born, and this is not what I expected. So then we decided, okay, what's going on? So if you detrend the data back to 1980, the map in the middle there is the sea surface temperature anomalies detrended. So as if that event had happened in a climate of 1980. And then on the right is the trend itself, so what you get by subtracting those two. So the detrended has a strong, obviously, El Nino event, stronger than what actually happened, and that's because the trend is cooling. There's a slight cooling trend in the tropical Pacific since 1980. That's a whole interesting subject in itself, and I would say the jury is still out on what has driven that cooling trend. So then we repeated our atmospheric model experiment, and we prescribed the sea surface temperatures from the with the detrended data. And again, did 50 runs, so we know this is the model's response. And yeah, I saw somebody smile. It's like, okay, that's what we expected, or I expected. That blue area in the North Pacific, that's a deepening of the Aleutian low. That's an intensification of that low pressure system. And it's very pronounced. I think it was something like 10 hectopascal. And that would fit with the canonical picture or based on compositing previous events. And then the trend is really driving the opposite sign, and they're largely canceling. They're largely offsetting one another. So climate change, or maybe partly internal variability that's behind this trend, and then partly this differential warming pattern in the trend where you have the Atlantic and the Indian Oceans warming relative to the Pacific, can really affect then the final, the response of the Aleutian low to those sea surface temperatures. And then, not surprisingly, that has ramifications for precipitation over North America. So here, just showing that same layout of plots, but now the bottom row, we're showing that the model's atmospheric model precipitation response instead of the sea level pressure. And so there's a lot of dots on the map on the left, meaning even with 50 runs, we cannot distinguish the El Nino-driven impact from just random internal variability that exists in the atmosphere. But then if you look at that middle map on the bottom, you see, very significant and wetter conditions over California and the whole southern tier of the US, especially the southeast US, and then drying to the north. And then you can look at the lower right, and you can see that, again, the impact of the SST trend is largely offsetting the impact from the El Nino event. So what does this mean for this coming winter? I don't know, but it's just these are the factors at play. We have now a quite certain forecast of a very strong, if not exceptionally strong event. But in December, January, February, that percentage went down to 51%. So maybe we're in that strong category, not the exceptionally strong. Secondly, what kind of teleconnection will that drive? That depends on what else is happening in the atmosphere, independent of El Nino. And it also depends on, that this background climate change is still happening. So, what to tell your families and relatives whether they should fix their roof in Southern California. I think it's really important to just give these nuances that we know are behind what kind of impacts we should expect. Okay, thanks very much. Happy to take questions. I have no idea what the timing is, but we'll take a few. Okay, good. Yeah.
On the last slide, this one. It looks like the precip effects from the detrended and the trend, if you add those two together, it gives you the full. Is that expected that they would just combine like that?
Yeah, it's a great question. So in fact, it's built in the way that I did these maps. So on the left is when we prescribed the actual SST anomalies. And then the middle, we detrended and did the experiment with those. And then I actually obtained those maps on the right by subtraction. So they do add up for that reason. But then later in the process of doing this research, we actually did runs with the trend, specifying this trend pattern itself. And we got something that looks like that lower map, but the amplitudes were, I think they were kind of a bit weaker. So there's some nonlinearities that are going on that remain to be explored. So in this case, it is built in. Thank you for that. That's a great observation. Yep.
Curiosity, if we are making this plot with La Nina conditions, would it be opposite pattern?
Awesome. To pick up on that, the answer is yes. So Nat Johnson and Michel Lheureux, I think I mentioned them. They're the NOAA CPC folks. They wrote a very nice paper. It's still under review, and they did this kind of experiment for this El Nino, and they did it for the subsequent La Nina, and then separated the role of background trends from the El Nino, La Nina itself. And indeed, just as we speculated, the La Nina teleconnections and climate impacts were exacerbated by the trend. And that's just what we would expect, right? If the trend pattern drives, drying over the West Coast, which is kind of a La Nina impact, if you also have a La Nina event, you're going to enhance those impacts. So things may become more asymmetric in terms of impacts between El Nino and La Nina if this differential warming trend continues. Yeah.
Thanks for your talk.
Welcome.
I'm an expert on ENSO. I was interested in the time series of the last 50 years, probably when you show like approximately 6 strong events.
Yeah.
And those were above 2 degrees, I think. But if we see like the opposite side, like La Nina,
yeah.
I don't see anyone below
Yeah.
that threshold. So
Yeah.
personal bias, like seeing this, like it seems that we can reach higher like positive anomalies,
Yes.
but it seems that we don't have like the same symmetry, right? We don't have the symmetry here.
Yeah, that's an accurate statement. Why are El Nino events stronger than La Nina? Off the top of my head, I wish I had a really good answer. There's a lot of asymmetries that I would say research in the last 15 years really have shown. One asymmetry is in the amplitude. El Niños can reach higher values than La Niñas, in opposite sense. Another asymmetry is how long the events last. So El Nino events tend to last a year. La Niñas can last 2 or 3 years. So part of the trade-off between amplitude is duration. And so actually these La Nina events, it just takes longer to recharge the warm water beneath the surface. So it can't grow as fast, the La Nina events, but it can last longer. And then the third asymmetry is in the spatial, the spatial expression of SST anomalies. La Nina negative anomaly, SST anomalies during La Nina tend to expand farther west than the positive anomalies during El Nino. So that's also a very important aspect because it can affect the teleconnections as well. So there's definitely, you don't want to treat El Nino and La Nina, completely symmetrically. Yeah, good question. Yeah.
Questions. One is about the background climate change you mentioned for the cooling trend for the Pacific. Do you think that more comes from like the internal ocean variability or like global warming or aerosol change? And the second question is that for the La Nina and the El Nino events, like with the climate change, global warming, and aerosol, what direction they tend to change or they will not change? And it's like more multi-year La Nina or stronger El Nino events are there?
Yeah, great questions. And these are all just cutting edge research questions. I don't think they've been settled fully settled. But the first question, what is driving that pattern of differential warming in the trend? I think we're now maybe able to say in very rough terms, half is externally forced by that combination of greenhouse gases, the way that aerosols have changed, and also stratospheric ozone in the southern hemisphere. And then about half is likely coming from the negative phase of the Pacific decadal variability phenomenon. And I don't think we can say more precisely than that. So I think both contribute. And I say this, I can talk to you more in detail and give you references, but this is cutting edge work right now, and people are really trying to quantify those numbers. And then for your second question, which is great, you know, again, there's so much uncertainty if you across models how El Nino and La Nina's event characteristics may change going forward. Most models indicate that El Nino events will become stronger, but it can also become more oscillatory. So we may have fewer neutral years in between El Nino and La Nina episodes. But whether we are actually seeing that as a factor in this current upcoming El Nino or the current one, I think we cannot say with any confidence that climate change is impacting the strength because there actually were some events, 2 events prior to 1950 that were roughly 3 degrees C anomalies. But these are all really important questions. ENSO is a very delicate balance between all these factors that create this phenomenon. And models have different balances of these different factors. And there's a lot of intermodal spread, if you will, in the future, the projections of ENSO behavior going forward. So a lot of work needs to be done. I hope some of you will do it.
Okay, in the interest of time.
Yeah. I would love to stay. My pleasure. Yeah.
Okay, so to continue the discussion, Clara can stay a few minutes after. I'm going to do a really quick check-in before I send you off to the second part of the lab here. I'm not sure that I need my slides, but you can bring them up if you like. I just want to say that, well, I guess if anyone has a burning question about the lab, you can bring it up now, but feel free to have conversations with all the helpers in the lab session. Yeah, and I just want to remind you, so we were dealing with some issues on Jupyter Hub. Make sure to use the tutorial queue instead of the Casper queue as it says in the instructions. So you're not waiting for a long time to sign into, using On Demand to sign into Jupyter Hub. Other than that, I just want to remind you at 4:20, we're going to come back in here for the debrief. But other than that, I'll release you to the library.
Oh, thanks, Claire, again.
I have a question.
Yeah.
Sarah, by
Hi,
the
Sarah.
way.
Nice to meet you.
I